33.3 billion years. That's it. That's the number. The universe, everything that exists, everything that has ever existed, every star, every planet, every atom, every thought, every civilization that has ever risen or will ever rise, has a lifespan. And that lifespan is 33.3 billion years. Not approximately, not a very long time. A physicist sat down with the latest data from the most sophisticated astronomical instruments ever built, ran the calculations, and came back with a number. A specific, almost unsettling number, like an expiration date stamped on the bottom of everything. Think about what that actually means for a second. The universe isn't eternal. It isn't infinite. It had a beginning, the Big Bang, roughly 13.8 billion years ago, and it has an end, a real end. Not a slow fade into cold darkness, not an endless thinning into nothing, but a collapse, a reversal. Everything that has been expanding for 13.8 billion years will eventually slow down, stop, and fall back in on itself, collapsing into a single point of infinite density. Physicists call it the Big Crunch. It's exactly what it sounds like. And here's the part that should stop you completely. The universe is 13.8 billion years old. The total lifespan is 33.3 billion years. That means we're not near the beginning. We're not watching a young universe in its infancy with everything still ahead of it. We're sitting at roughly the 40% mark. We are almost halfway through. The universe is middle-aged, and we just figured that out in 2025. From data collected by a machine in the Arizona desert pointing at galaxies so distant that their light left before the Earth existed. You found the receipt, and it has a due date on it. Now. Before you decide this is just another "the universe is big and scary" video, I want to be clear about something. This isn't speculation. This isn't a thought experiment or a philosopher's riddle or a science fiction premise. This is a peer-reviewed calculation published in the Journal of Cosmology and Astroparticle Physics in 2025, produced by physicists at Cornell University, Shanghai Jiao Tong University, and other institutions, using real data from two of the most ambitious astronomical surveys ever conducted. The Dark Energy Survey and the Dark Energy Spectroscopic Instrument, DESI, a machine that spent 5 years mapping 47 million galaxies to understand the single most mysterious and most dominant force in the universe. The force that is, depending on what it's actually doing right now, either going to let the universe keep expanding forever or bring the whole thing crashing back down. That force is called dark energy. And this video is about what it is, how we found it, what it's doing to the universe, and what it means that a physicist just ran the numbers and told us that everything, all of it, ends in approximately 33.3 billion years. Let's start with a question that sounds simple and isn't. What is the universe doing right now? Not on the scale of planets or solar systems or even galaxies. On the largest scale you can possibly imagine. The scale of the universe itself. What's happening? The answer, which humans didn't know until 1998, is that the universe is expanding. Not just expanding, accelerating. Getting bigger, faster and faster, as if something is pushing it from the inside. Every galaxy is moving away from every other galaxy. The farther apart two galaxies are, the faster they're receding from each other. And that recession speed is increasing over time. Right now, as you're watching this, the universe is larger than it was a second ago. And it's expanding slightly faster than it was a second ago. And it will be expanding slightly faster still a second from now. This has been happening for roughly 5 billion years, and nothing we know of is going to stop it anytime soon. The thing doing the pushing, the thing that accounts for 68.3% of everything in the universe, more than all the stars and planets and dark matter and atoms combined, is dark energy. You've probably heard the name. You almost certainly don't know what it is, because nobody does. Not even the physicists who named it. Michael Turner, the University of Chicago cosmologist who coined the term in 1998, said it as plainly as it can be said. I think dark energy is the most profound mystery in all of science. Until we understand it, we can't sensibly speculate about the destiny of the universe. Notice what he didn't say. He didn't say, one of the more interesting open questions. He said, the most profound mystery in all of science. The man who invented the word for it is telling you it's the thing we understand least about everything. And yet, it controls the fate of the universe. Its behavior, whether it stays constant, whether it weakens, whether it changes over time, determines whether the universe expands forever, tears itself apart, or collapses back into a singularity. The expiration date on everything is written in dark energy's behavior. And dark energy is something we cannot identify, cannot detect directly, and cannot currently explain from first principles. That's the situation. The dominant force in the universe is a complete mystery. Its behavior dictates the fate of everything. And in 2025, using the best data ever collected about it, a physicist at Cornell University calculated that it's weakening, and that the weakening, if real, puts the universe on a trajectory toward a very specific and very final end. So here's how this video works. We're going to build this story from the ground up. We're going to start with what the universe is actually made of, because most people have never truly felt the absurdity of the cosmic recipe. We're going to go back to 1998, when two rival teams of astronomers accidentally discovered dark energy while looking for something completely different. And we're going to sit in the room with them when they realized what they were looking at. We're going to dig into what dark energy might actually be, including the fact that the leading theoretical explanation for it is, and this is an actual description used by physicists, the worst prediction in the history of science. We're going to look at the crack that appeared in the standard cosmological model in 2025, when a machine that spent 5 years counting 47 million galaxies came back with data suggesting dark energy might not be constant, that it might be weakening, and what that means for the expiration date. We're going to walk through what the end of the universe actually looks like, step by step, on a timeline. And then, at the end, we're going to sit with what it means that we know this, that we live in a universe with a knowable lifespan, that we happen to exist at the 40% mark, and that we're the first species in the history of this universe, as far as we know, capable of reading the clock. But first, let's make sure you actually feel what 33.3 billion years means. Numbers at this scale are almost impossible for the human brain to process. We evolved to count things in the dozens, track seasons in the hundreds, think in generations of decades. Billion-year timescales are structurally outside the range of human intuition. So let's use some anchors. The universe is 13.8 billion years old. Human civilization, cities, writing, agriculture, everything, is about 10,000 years old. That's 0.00007% of the universe's current age. The entire span of human history, everything from the first cave paintings to the last website you visited, fits into a rounding error on the cosmic timeline. The Sun formed about 4.6 billion years ago. It has about 5 billion years of hydrogen fuel remaining before it exhausts its core and expands into a red giant that will likely swallow the Earth. That event, the death of our star, the end of any life on this planet, is still 5 billion years away. It sounds far. On the cosmic calendar, it's next Tuesday. The Andromeda Galaxy, the nearest large galaxy to ours, a swarm of roughly 1 trillion stars, currently about 2.5 million light-years away, is on a collision course with the Milky Way. That collision begins in roughly 4.5 billion years. The two galaxies will merge over hundreds of millions of years, their stars mostly passing through each other, but the whole structure being reshaped into something unrecognizable. That's also next Tuesday, cosmically speaking. Complex multicellular life on Earth has existed for about 600 million years. Modern humans for about 300,000. The gap between our species' first appearance and now, all of human evolution, all the generations, all the history, is 300,000 years. Against the 33.3 billion year lifespan of the universe, that's roughly 0.001%. So when we say the universe is 40% through its lifespan, we're saying something that should feel both abstract and immediately personal. Because 40% is not nothing. 40% is not the beginning. We are not at the start of an endless story. We are at the point in the story where the shape of the ending is becoming visible. And the ending, according to the 2025 calculation, looks like this. For the next several billion years, the universe continues expanding and accelerating, roughly as it does now. Dark energy continues to push galaxies apart. Our local group of galaxies, the Milky Way, Andromeda, a few dozen smaller galaxies, will remain gravitationally bound together, eventually merging into one large elliptical galaxy. But everything outside our local group will recede faster and faster. Distant galaxies will cross our cosmic horizon, the boundary beyond which space is expanding faster than light, and disappear. Not destroyed, just gone, unreachable. Their light can never reach us again. The night sky gets darker as the millennia pass. Then, in approximately 11 billion years from now, the expansion stops. Just stops. Dark energy, which has been driving the acceleration, reaches a turning point in the time model. The underlying physics flips. The force that has been pushing everything apart begins to lose its grip. The expansion rate drops to 0. The universe reaches its maximum size. And then it begins to contract. Slowly at first, imperceptibly. But gravity, which has been losing the tug-of-war against dark energy for 5 billion years, reasserts itself. Space begins to collapse. The distances between galaxy clusters start shrinking. The temperature of the universe, which has been dropping for 13.8 billion years as the expansion spread energy thinner and thinner across a growing volume of space, begins to climb again. As the universe contracts, things get hotter. The contraction accelerates. Galaxy clusters that were moving apart are now falling toward each other. Individual galaxies begin to merge. Stars crowd together in ways they never have before. The cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space at a temperature just 2.7 degrees above absolute zero right now, begins to warm. Its wavelengths shorten as space contracts, the reverse of the redshifting that stretched them over billions of years of expansion. Then things get violent. As the universe contracts further, the background temperature exceeds the surface temperature of stars. Stars, which radiate heat into a cooler surrounding universe, suddenly find themselves in an environment hotter than they are. They can no longer lose heat. They begin to disintegrate. First, the outer stars in galaxies, then more. The distinction between inside a star and outside a star starts to blur as the surrounding temperature approaches stellar conditions everywhere. Eventually, the whole universe is as hot as a stellar interior. Every structure, planets, moons, asteroids, any remnant of what existed, is vaporized. Matter itself breaks down into its constituent particles as temperatures rise toward the conditions of the early universe, now running in reverse. And then, approximately 20 billion years from now, roughly 33.3 billion years after the Big Bang, everything collapses into a single point. The Big Crunch. The end of space, the end of time, the end of everything. That's what the receipt says. Now, before you spiral completely, there are things you need to know about this prediction. Important caveats. Because science is not in the business of certainties, and this calculation, striking and specific as it is not a confirmed fact. It's a model, a carefully constructed model, built on real data, peer-reviewed and published, but a model nonetheless. The DESI data that underpins it has not yet reached the 5 sigma confidence level that physics requires before claiming a discovery. The full 5-year DESI dataset, the most comprehensive dark energy data ever assembled, was completed on April 14, 2026, and the first results from that complete dataset are expected in 2027. Those results could strengthen the prediction, refine it, or show that the hint of weakening dark energy was a statistical fluctuation that fades away with more data. Several major instruments coming online in the next few years, the Nancy Grace Roman Space Telescope, whose launch is targeted for early September 2026, and ESA's Euclid satellite, already in operation, will provide independent measurements that either corroborate or challenge the picture. So the expiration date might move. It might disappear entirely. The clock might be wrong. But here's what is not wrong. Dark energy is real. The accelerating expansion is real. The fact that dark energy's behavior determines the ultimate fate of everything is real. And the fact that we are now, for the first time in human history, building instruments sensitive enough to actually measure whether dark energy is changing, sensitive enough to read the fine print on the receipt, is also real. We are living in the specific window of cosmic time when humanity first became capable of asking the question, how does this end? We might be getting the first real answer, and the answer might be in about 19.5 billion years, give or take. Everything you're about to learn about what dark energy is, where it came from, how it was discovered, what it might be doing right now, and what the instruments of 2026 and 2027 are going to tell us, all of it connects back to this number. 33.3 billion years. Every piece of the story is a piece of understanding the clock. So let's start at the beginning. Not the Big Bang. We'll get there. Let's start with the ingredients. Because before you can understand why the universe might end, you need to understand what the universe is actually made of. And the answer to that question is one of the most disorienting facts in all of science. Let's do something that sounds simple. Let's figure out what the universe is made of. Not the exotic stuff, not black holes or neutron stars or quasars, just the basic inventory. If you could take everything that exists, every particle, every form of energy, every component of the cosmos, from the smallest subatomic wobble to the largest supercluster of galaxies, and weigh it all up, what would you find? You'd find that you recognize almost none of it. Here's the breakdown. Normal matter, atoms, the stuff of the periodic table, protons and neutrons and electrons. Every element from hydrogen to uranium, every molecule that has ever been assembled into anything, every star, every planet, every ocean, every living cell, every thought that has ever been thought inside a brain made of atoms, accounts for 4.9% of the total mass energy content of the universe. 4.9%. Let that sit for a moment. Everything chemistry has ever studied, everything biology has ever catalogued, everything physics has ever put in a particle accelerator and smashed apart. Every galaxy you've ever seen in a photograph, all of it, combined. Less than 5% of what exists. The remaining 95.1% falls into two categories, and we have no idea what either of them is. About 26.8% is dark matter, the invisible scaffolding that holds galaxies together, the missing mass that keeps stars from flying off into the void, the subject of 100 underground detectors that have been waiting decades for a single signal that hasn't come. We covered dark matter in another video, and it's its own extraordinary mystery. For now, just hold the number, 26.8%. Real, everywhere, unknown. And then there's the rest, the biggest slice, the dominant ingredient, the thing that makes up 68.3% of everything that exists. Dark energy. These are the numbers from the European Space Agency's Planck satellite, which spent years mapping the cosmic microwave background, the oldest light in the universe, with extraordinary precision, and delivered its final cosmic recipe in 2013. The numbers have been refined since, and they haven't changed in any meaningful way. This is the composition of the universe, measured with the best instruments humanity has ever built. Normal matter, 4.9%. Dark matter, 26.8%. Dark energy, 68.3%. If the universe were a 100-piece jigsaw puzzle, dark energy would be 68 of the pieces. And we don't know what any of those pieces show. We don't know what dark energy is made of. We don't know what produces it. We don't know whether it's a particle, a field, a property of space itself, or something that doesn't fit into any category physics has ever developed. We know its effects. We know what it does to the universe on the largest scales. But what it actually is, at the level of fundamental physics, is completely unknown. That's the dominant ingredient in reality. And before we go any further, I want to make sure you feel how strange that is. Because there's a tendency, when confronted with numbers like these, to nod along and move on. 95% unknown. Sure, science is hard. Next slide. But I don't want you to move on yet, because this is the foundational weirdness that everything else in this video sits on top of. Think about how science works. We learn about the world by observing it, measuring it, running experiments on it. Chemistry works because atoms interact with each other and with light in ways we can detect and study. Biology works because living things are made of molecules that we can isolate and examine. Physics works because particles and forces produce measurable effects that we can capture in detectors and describe with equations. The entire edifice of scientific knowledge rests on the assumption that things can, in principle, be observed and understood. Dark energy violates that assumption at the most fundamental level. It doesn't interact with light. It doesn't interact with atoms in any way that any instrument has ever detected. It doesn't cluster or clump or leave a local signature. It doesn't do anything you can point a detector at and measure directly. Its existence is inferred entirely from its effect on the universe at the largest possible scale, the fact that the expansion is accelerating. Take away that one observation and dark energy vanishes from physics entirely. We know it's there the same way you'd know there was a fan in a sealed room, not by seeing the fan, but by watching what it does to everything else. And we've never opened the room. Now, to really understand dark energy, what it might be, why it behaves the way it does, and why it's connected to the expiration date of the universe, you need to understand three things. What the universe was doing before dark energy took over, what changed roughly 5 billion years ago, and why empty space might not actually be empty. Let's take them in order. For the first several billion years after the Big Bang, the universe was expanding, but gravity was winning. Not winning enough to stop the expansion. The initial outward momentum from the Big Bang was too strong for that, but winning enough to slow it down. The expansion rate was decreasing over time. If you'd asked a cosmologist in 1990 what the universe's future looked like, they would have said it depends on how much matter there is. If there's enough mass, gravity eventually stops the expansion and the universe collapses. If there isn't enough, it expands forever, but at a slower and slower rate, eventually approaching zero, but never quite stopping. Either way, the expansion decelerates. That was the expectation. Deceleration was written into the physics. What nobody expected was a third option. What actually happened, starting roughly 5 billion years ago, is that the expansion stopped decelerating and began accelerating. The brake came off and a gas pedal appeared. Something shifted in the fundamental behavior of the cosmos, and the universe stopped slowing down and started speeding up. The culprit, we now know, was dark energy achieving dominance. For the first several billion years of the universe's history, the density of matter was high enough that gravity outweighed dark energy's influence. But as the universe expanded, matter's density diluted, spread thinner and thinner across a growing volume of space, while dark energy, if it's the cosmological constant, stayed at a fixed density. Eventually, dark energy won. The scales tipped, and the universe has been accelerating ever since. Think about what that transition means for the expiration date we established in Section 1. The Big Crunch prediction in the time model depends on dark energy weakening over time, losing its grip, declining in strength, eventually allowing gravity to reassert itself and reverse the expansion. The transition we just described, from deceleration to acceleration, happened when dark energy grew strong enough to dominate. The time model is predicting the reverse transition, dark energy weakening until matter dominates again, and then the long collapse begins. Same basic mechanism, same fundamental balance between gravity and dark energy, just playing out in reverse. To understand why that's plausible and why it's so hard to measure, you need to understand what dark energy actually is, at least in the leading theoretical framework. And that framework starts with one of the strangest ideas in all of physics. Empty space is not empty. This is not a metaphor or a philosophical provocation. It's a testable prediction of quantum field theory, the most precisely verified scientific theory in human history, accurate to more decimal places than any other physical theory ever developed. And what quantum field theory says about empty space is this: even in a region of space with no particles, no radiation, no matter of any kind, there is still energy. The vacuum itself has an energy density. Quantum fields, the fundamental entities that quantum field theory describes, cannot be completely zero even in their ground state. They fluctuate, constantly, randomly, producing pairs of virtual particles that pop in and out of existence too briefly to be directly detected, but real enough to have measurable physical effects. This vacuum energy, the energy inherent to empty space itself, is the leading candidate for what dark energy actually is. Einstein's cosmological constant, the mathematical term he introduced in 1917 and later abandoned, is exactly this: a constant energy density distributed uniformly throughout all of space. If empty space has energy, and if that energy density is constant, doesn't dilute as the universe expands because space itself is what carries it, then it produces exactly the kind of repulsive gravitational effect that dark energy is observed to produce. As the universe expands, there's more space, which means more vacuum energy, which means the repulsive effect grows relative to the diluting matter, which means the expansion accelerates. It fits. The cosmological constant fits the observations beautifully. It explains the acceleration, matches the Planck satellite data, and reproduces the large-scale structure of the universe in computer simulations with impressive accuracy. There's just one problem. One absolutely catastrophic, civilization-shaking, keeps physicists up at night problem. When you actually calculate the vacuum energy using quantum field theory, when you sit down with the equations and work out what the energy density of empty space should be, the answer you get is approximately 10 to the power of 120 times larger than what we observe. 10 to the power of 120. I need you to understand how large that number is, because your brain is going to try to treat it like any other big number and move on, and you can't let it do that. The number of atoms in the observable universe is estimated at around 10 to the 80 power. That's already a number so large it's essentially meaningless to human intuition. 10 to the power of 120 is not just larger than that, it's incomparably, catastrophically, absurdly larger. It's larger than 10 to the power of 80 by a factor of 10 to the power of 40. If you took the number of atoms in the observable universe and raised it to the power of the number of atoms in the observable universe, you'd still be nowhere near 10 to the power of 120. And that's the factor by which quantum field theory's prediction for vacuum energy misses the observed value of dark energy. Quantum theory, the most successful, most precisely tested theory in the history of science, looks at empty space and predicts a vacuum energy density that is 10 to the power of 120 times larger than what's actually there. This isn't a rounding error. This isn't a small correction that further work might fix. This is the single largest discrepancy between a theoretical prediction and an experimental measurement ever recorded in the history of physics. It has an official name, the cosmological constant problem. And physicists don't call it a problem the way they'd call a tricky calculation a problem. They call it a catastrophe. The vacuum catastrophe. Because if the vacuum energy were anywhere near as large as quantum theory says it should be, the universe would have expanded so violently in the first moments after the Big Bang that no atoms, no stars, no galaxies, no planets, no life could ever have formed. The expansion would have been so ferocious that matter would have been shredded apart before it could assemble into anything. The universe would be a cold, thin, featureless void of almost infinite size. It's not that, obviously. So something is cancelling out almost all of that vacuum energy, leaving only the tiny, gentle, cosmological constant that we observe. And nobody knows what that something is. No physical mechanism has ever been identified that could produce a cancellation of this precision. Some physicists have spent entire careers on this problem. It remains completely unsolved. So that's the state of our understanding of dark energy's most likely identity. The leading explanation is vacuum energy. The leading calculation of vacuum energy is off by 10 to the power of 120. And nobody knows why. This is what's running the universe. This is what's driving the acceleration. This is the force whose future behavior determines whether the expiration date is real. Now, the cosmological constant isn't the only candidate. There's a competing idea called quintessence, from the ancient Greek fifth essence, the mysterious substance the Greeks believed filled the heavens beyond the four earthly elements. Quintessence, in modern cosmology, is a dynamic field that pervades the universe the way a magnetic field pervades space. Except, instead of affecting charged particles, it affects the expansion rate of the universe itself. Unlike the cosmological constant, quintessence can change over time. Its energy density isn't fixed. It evolves as the universe evolves. This is important for the expiration date. The cosmological constant, being constant, would push the universe apart forever. A universe with a true cosmological constant doesn't end in a big crunch. It just keeps expanding, getting colder and emptier, until it reaches a state of maximum entropy, heat death, the long freeze, hundreds of trillions of years from now. No crunch, just a slow, cold fade. But quintessence, a dynamic dark energy that evolves, weakens, potentially reverses, could produce the crunch. If dark energy isn't constant, but is instead a field that changes over cosmic time, it could weaken over billions of years, gradually lose its repulsive influence, and eventually allow gravity to win. That's the scenario the TIE model is built around. That's what the DESI data hints at. And that's what turns 33.3 billion years from a philosophical abstraction into a physical prediction with a mechanism. Here's the thing about distinguishing between these two options, cosmological constant versus quintessence. It's extraordinarily difficult. The difference between a truly constant dark energy and one that changes very slowly is tiny. Too small to detect with the instruments available in the early decades after the 1998 discovery. You need to measure the expansion rate of the universe at different points in cosmic history to compare how dark energy behaved 3 billion years ago versus 6 billion years ago versus 9 billion years ago, with sufficient precision to see whether the value changes or stays fixed. That's exactly what DESI was built to do. That's why it spent 5 years measuring 47 million galaxies. That's why it tracked dark energy's influence across 11 billion years of cosmic history. And that's why its results, the hints of weakening dark energy, the suggestion that the cosmological constant might not be constant after all, are so significant. But we're getting ahead of ourselves. Before we get to DESI and the crack in the model and the specific calculation that produced our expiration date, we need to go back to the beginning of this whole story. Back to 1998. Back to the moment when two rival teams of astronomers working in secret from each other both discovered something that nobody was looking for. Something that shook cosmology at its foundations. Something that every physicist who first heard about it assumed was a mistake. Because dark energy wasn't discovered by someone looking for dark energy. It was discovered by accident, by people looking for something else entirely, using dead stars as measuring sticks across billions of light years of space. It's one of the great accidental discoveries in the history of science. And the story of how it happened is one of the most dramatic scientific narratives of the 20th century. It's 1988. Ronald Reagan is in the last year of his presidency. The Berlin Wall is still standing. The Internet doesn't exist in any form recognizable today. And at Lawrence Berkeley National Laboratory in California, a young physicist named Saul Perlmutter is setting up what he hopes will be a clever, methodical, decade-long project to measure one very specific number. Not dark energy, Nobody was thinking about dark energy. The concept didn't even have a name yet. What Perlmutter wanted to measure was the deceleration of the universe. Here's the thinking. The Big Bang sent everything flying outward. The universe has been expanding ever since. But everything in the universe has mass, and mass generates gravity, and gravity pulls things together. So the expansion should be slowing down. It has to be slowing down. The only question, the interesting cosmological question of the era, was by how much? Was there enough matter in the universe to eventually stop the expansion entirely and pull everything back together? Or was there too little, meaning the universe would expand forever, but at a steadily decreasing rate? The answer to that question would tell you the ultimate fate of the cosmos. To find the answer, you needed to measure how fast the universe was expanding at different points in its history. If expansion was faster in the past and slower now, you'd have your deceleration. The size of the slowdown would tell you how much gravitational braking the universe's matter was providing. The trick was finding a way to measure cosmic distances accurately enough to track the expansion rate across billions of years of history. And the solution Perlmutter's team, the Supernova Cosmology Project, settled on was one of the most elegant in the history of observational astronomy. Exploding stars. Specifically, a type of stellar explosion called a Type 1a supernova. Understanding why this works requires a brief detour into stellar physics, and I promise it's worth it. When a star like our Sun reaches the end of its life, it eventually sheds its outer layers and leaves behind a dense, Earth-sized remnant called a white dwarf. A white dwarf is essentially a dead star, no longer fusing hydrogen in its core, just a hot, dense ball of mostly carbon and oxygen sitting in space, slowly cooling over billions of years. On its own, a white dwarf is inert. Fascinating, but inert. But sometimes a white dwarf isn't alone. Sometimes it has a companion, another star orbiting close by. And if the companion is close enough, the white dwarf's gravity can pull material off the companion's surface, slowly accumulating mass over millions of years. The white dwarf gets heavier, and heavier, and heavier. There's a limit. When a white dwarf accumulates enough mass, a very specific limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun, something dramatic happens. The white dwarf's internal pressure can no longer support the weight of all that accumulated material. The whole thing undergoes a runaway thermonuclear explosion. Every atom in the white dwarf fuses almost simultaneously. The explosion releases as much energy as the Sun will produce in its entire 10 billion year lifetime, in a few seconds. That's a Type 1a supernova. And because the explosion always happens at the same threshold mass, the Chandrasekhar limit, Type 1a supernovae always explode with roughly the same intrinsic brightness. They're what astronomers call standard candles. You know how bright they actually are. So when you observe one and measure how bright it appears, you can calculate how far away it is. The dimmer it appears, the farther away it is. Simple geometry. This is the key. If you can find Type 1a supernovae at different distances, different cosmic distances corresponding to different points in the universe's history, and measure how bright they appear, you can reconstruct the expansion history of the universe. You can see whether the universe was expanding faster or slower in the past. You can measure the deceleration. That was the plan. A brilliant plan. A plan that Perlmutter started executing in 1988. It was slow going at first. Supernovae are rare and unpredictable. You can't point a telescope at a specific star and wait for it to explode. You have to monitor enormous numbers of galaxies simultaneously, checking them repeatedly for the telltale brightening that signals a supernova. Moving fast because supernovae fade within weeks. The technology of the late 1980s made this extraordinarily difficult. But Perlmutter's team developed systematic methods, ways of finding and following supernovae at scale that hadn't existed before. They were building a new methodology as much as conducting observations. By the early 1990s, the Supernova Cosmology Project had a working pipeline. They were finding supernovae, measuring their apparent brightness, building their dataset. And then, in 1994, something annoying happened. A rival team appeared. Brian Schmidt, an astronomer at the Australian National University, launched a competing project, the High-Z Supernova Search Team. High-Z because they were looking at high redshift supernovae, supernovae so far away that the expansion of the universe had stretched their light toward the red end of the spectrum, a phenomenon called redshift that tells you how fast something is receding. The further away a galaxy, the faster it's moving away, the more its light is redshifted. High-Z meant far away. Far away meant looking far back in time. Schmidt's team included a young astronomer named Adam Rees, who would end up being the person who first saw what the data was actually saying. Now there were two teams, both using the same basic technique, both looking at the same targets, distant Type 1a supernovae, both racing to publish results. They weren't sharing data. They weren't collaborating. They were competitors. And in science, competition is sometimes exactly what's needed to push things forward. Each team drove the other to work faster, check more carefully, be more rigorous, because the last thing either group wanted was to publish a result that the other team immediately disproved. The rivalry had an edge. Perlmutter's group had been at this for 6 years by the time Schmidt's team started. They had the methodology, the pipeline, the head start. Schmidt's group had something else, the conviction that the technique could be done better, faster, with more attention to controlling systematic errors. For several years, both teams worked in parallel, finding supernovae, measuring distances, building their datasets. The expectation in both camps, the assumption baked into the entire design of both projects, was that they were going to measure deceleration. The only question was whether deceleration was strong enough to eventually reverse the expansion, or just slow it asymptotically toward zero. That was the interesting cosmological question. Deceleration was a given. It wasn't a given. By 1997, Perlmutter's team had accumulated enough data for a preliminary result. They published an analysis suggesting the universe might be decelerating at a rate consistent with a flat, matter-dominated cosmos, perhaps even showing some very slight deceleration. It was inconclusive, but it pointed in the expected direction. Fine. More data needed. Press on. Then the new data came in. Adam Rees was the person who ran the analysis for the High-Z team in late 1997 and early 1998. He was working through the numbers on the distant supernovae, measuring their apparent brightness, calculating their distances, comparing those distances to what a decelerating universe would predict. The supernovae were too dim. Not slightly too dim. Systematically, consistently too dim, in a way that couldn't be explained by dust absorption or supernova evolution, or any of the known systematic effects the team had carefully controlled for. Too dim meant too far away. Too far away meant the universe had expanded more than expected since those supernovae exploded. More expansion than expected meant the expansion had been faster in the past and was slowing down. Wait. No. That's not what too far away means. Sit with the geometry for a second, because this is the part where everything flips. If the expansion were decelerating, slowing down over time, then in the past, when those distant supernovae exploded, the universe would have been expanding faster than it is today. That means the universe would have been smaller than you'd expect when the light left those distant supernovae. Smaller means the supernovae would be closer than you'd predict from a simple extrapolation of today's expansion rate. Closer means brighter. The supernovae should have been too bright if the universe were decelerating. They were too dim. Too dim means too far away. Too far away means the universe was smaller and expanding more slowly in the past than you'd expect. More slowly in the past, faster now. Acceleration, not deceleration. Rees ran the numbers again. And again. He looked for every possible systematic error. Dust that could absorb light and make supernovae appear dimmer than they are. Differences in supernova chemistry at high redshift that could affect their intrinsic brightness. Gravitational lensing effects. Statistical flukes. He and his colleagues worked through every alternative explanation they could construct. The result didn't go away. The universe was not decelerating, it was accelerating. Something was pushing the expansion faster over time, not slowing it down, speeding it up. Robert Kirshner, who had supervised Rees as a doctoral student and was a senior member of the High Z team, later described the mood when the result became undeniable. There was a word he used that captures it precisely. The discovery was, he said, alarming. Not exciting, alarming. Because this wasn't the discovery of something they'd been hunting. This was the discovery that something was deeply, fundamentally wrong with the picture of the universe that every cosmologist in the world was working within. The universe was supposed to be decelerating. The physics demanded it. Gravity was supposed to be winning. And gravity was losing, badly, to something nobody had accounted for. Meanwhile, across the country and across the scientific community, Perlmutter's team was looking at their own data and seeing the same thing, independently. Using different telescopes, different analysis methods, different datasets, different teams of people who hadn't spoken to each other about their results. Two rival groups who had spent years competing for the same scientific prize had both found the same impossible answer. The universe is accelerating. The High Z team published their result in September 1998 in the Astronomical Journal. Perlmutter's Supernova Cosmology project published their result in 1999 in the Astrophysical Journal, using 42 supernovae. Both papers reached the same conclusion. Both found that the most distant supernovae were dimmer than expected. Both found that the expansion of the universe was not slowing down. Science magazine named the discovery Breakthrough of the Year for 1998. And then came the question that nobody had a good answer for. If the expansion is accelerating, what is accelerating it? Gravity pulls things together. Whatever this was, it pushed things apart. It had to be some form of energy. Energy that permeates all of space, that doesn't dilute as the universe expands, that has a repulsive gravitational effect. Something embedded in the fabric of space itself. Michael Turner, the cosmologist at the University of Chicago, who was one of the first people to think seriously about what the accelerating expansion implied, needed a name for it. Dark matter already had its name, the invisible scaffolding of galaxies. This new thing was different, bigger, more pervasive, and even more mysterious. Turner called it dark energy, not because he knew what it was, because he needed something to call it while everyone figured out what it actually was. The name was a placeholder for an unknown. It still is. Now let's talk about Einstein, because this is the part of the story where a man who died in 1955 turns out to have been right about something he spent years being ashamed of, for reasons that have nothing to do with why he introduced it. In 1917, Einstein was working on the cosmological implications of his general theory of relativity, the theory of gravity he'd published 2 years earlier that described gravity not as a force, but as the curvature of space-time caused by mass and energy. When Einstein applied his equations to the universe as a whole, they produced a universe that couldn't stand still. The equations described a universe that was either expanding or contracting. It couldn't be static. But the universe, as far as anyone in 1917 could tell, was static. Stars were in fixed positions. The cosmos appeared unchanging. A dynamic universe, one that was growing or shrinking, seemed obviously wrong. So Einstein did something that in retrospect is both understandable and extraordinary. He added a term to his equations, a mathematical fudge factor, a constant. He called it the cosmological constant, denoted by the Greek letter lambda, that represented a uniform energy density throughout all of space, providing a repulsive effect that exactly balanced the gravitational attraction of matter and produced a static universe. It worked mathematically. The equations with the cosmological constant described a static universe. Einstein was satisfied. Then, in 1929, Edwin Hubble observed that galaxies were receding from each other. The universe was expanding. The static universe was wrong. The cosmological constant was unnecessary. Einstein dropped it from his equations. According to the physicist George Gamow, who wrote about a conversation with Einstein in a 1970 posthumously published autobiography, Einstein called the cosmological constant the biggest blunder of his life. Historians have debated whether Einstein actually used those exact words. No primary written source has been found, but his deep regret about the term is well documented in his published statements and correspondence. He died in 1955. 43 years later, in 1998, the teams led by Perlmutter, Schmidt, and Rees discovered that the universe's expansion is accelerating, and the simplest mathematical description of the thing causing that acceleration, the thing now called dark energy, is a uniform energy density throughout all of space, constant over time, producing a repulsive effect. In other words, the cosmological constant. The term Einstein invented in 1917 for the wrong reasons, abandoned in 1929, called his greatest mistake. It was the right answer all along. Not for keeping the universe static, which was the wrong goal and based on a wrong assumption, but as a description of the energy inherent to empty space that is driving the accelerating expansion of the universe. Einstein accidentally discovered dark energy in 1917 and then deleted his own discovery. Saul Perlmutter captured this perfectly. He wrote after the discovery, "Perhaps there was more insight in Einstein's blunder than in the best efforts of ordinary mortals." The cosmological constant is back. Lambda is back. Written in every modern cosmological equation, the standard model of the universe now goes by the name lambda CDM. Lambda, cold, dark matter, where lambda is Einstein's term, resurrected from the trash and promoted to the most important single symbol in cosmology. The symbol for the thing that controls the fate of everything, now. The 2011 Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe. Perlmutter received half the prize. Schmidt and Rees shared the other half. The Nobel citation read, "For the discovery of the accelerating expansion of the universe through observations of distant supernovae." It was, by any measure, one of the most consequential discoveries in the history of astronomy. The Nobel Committee described how the discovery had shaken cosmology at its foundations. Robert Kirshner, who had trained both Schmidt and Rees and contributed foundational work to the field, described it simply as no more waiting. The prize was right, the timing was right, the recognition was deserved. But here's something worth pausing on. The Nobel Prize was awarded 13 years after the discovery. 13 years during which the result was verified by independent methods, refined by better data, confirmed by the Planck satellite's measurement of the CMB, and built into the standard model of cosmology. Science moves carefully. It should move carefully. The 1998 result was extraordinary, and extraordinary results require extraordinary verification before they're woven into the fabric of accepted knowledge. The verification came. The result stood. The universe really is accelerating. And now, 26 years after the discovery, the question that the discovery immediately raised, what is dark energy exactly, is still unanswered. The cosmological constant is the best mathematical description we have, but it's not a physical explanation. It's a label, a placeholder, a way of fitting the equations to the observations without actually knowing what's producing the effect. To understand why that matters, and why it connects so directly to the expiration date and the Big Crunch prediction, you need to understand what dark energy would have to be at the level of fundamental physics. You need to understand why the leading theoretical candidate for dark energy is simultaneously the most successful and most catastrophically wrong prediction in the history of physics. You need to understand the vacuum catastrophe. And when you do, you'll understand not just why dark energy is mysterious, but why the mystery is so deep that some physicists consider it the most profound unsolved problem in all of science. Not one of the most profound, the most profound. The cosmological constant problem makes every other open question in physics look tractable by comparison. And it sits at the very center of our story. Because whatever dark energy is at a fundamental level, whatever mechanism produces it, is what determines whether it stays constant or changes over time. Whether it's the same forever or whether it weakens. Whether the universe expands forever into cold darkness or reverses, contracts, and ends in the violent singularity that a Cornell physicist calculated will arrive approximately 33.3 billion years after the beginning of everything. To get from here to there, we need to go somewhere unexpected. We need to go to empty space, and we need to look very, very carefully at nothing. Empty space is trying to kill the universe. Not metaphorically, not poetically. According to the best theory of matter and energy that humanity has ever produced, quantum field theory, the framework that underlies all of particle physics, the theory that predicted the Higgs boson decades before we found it, the theory that describes the behavior of electrons and photons with accuracy to more than 10 decimal places. Empty space contains energy. A lot of energy. So much energy that if it were actually present in the quantities the theory predicts, the universe would have expanded so catastrophically in its first moments that not a single atom would ever have formed. The universe would be an unimaginably vast, cold, empty void. It's not that. You know it's not that because you're sitting somewhere, made of atoms, watching this. So something is wrong. Either the theory is wrong, which would be extraordinary given how precisely it works for everything else, or something is cancelling out almost all of that vacuum energy, leaving only the tiny sliver that we observe as dark energy, through a mechanism that nobody has identified, that no theory has predicted, and that no experiment has ever shed light on. That's the cosmological constant problem. That's what sits at the center of our expiration date story. And to really feel the weight of it, to understand why physicists don't just call it a problem, but a catastrophe, you need to start from the beginning. You need to start with nothing. Here's what nothing actually is, according to quantum field theory. In classical physics, Newton's physics, the physics of everyday objects, empty space is genuinely empty. A vacuum is a vacuum. No particles, no energy, no fields. Just absence. The 0 point. The baseline. Quantum field theory changed that completely. In quantum field theory, everything in the universe, every particle, every force, is described as a vibration or excitation of an underlying quantum field. There's an electron field that permeates all of space, and electrons are excitations of that field. There's a photon field, and photons are excitations of that field. There are fields for quarks, for the weak force, for the Higgs. The entire content of the standard model of particle physics is a collection of quantum fields filling all of space simultaneously, overlapping, interacting, vibrating. And here's the crucial part. These fields cannot be completely quiet. Even in their lowest energy state, the vacuum state, the state with no particles, quantum fields still fluctuate. They have what's called 0 point energy, a minimum baseline vibration that cannot be removed even in principle because quantum mechanics forbids a field from being perfectly still. To be perfectly still would require knowing both the precise value of the field and its precise rate of change simultaneously, and Heisenberg's uncertainty principle prohibits that. So the vacuum isn't empty, it's seething. Constantly, everywhere, quantum fields are fluctuating at their minimum energy level, producing pairs of virtual particles, an electron and a positron, a quark and an antiquark, that pop into existence for an instant, too brief to be directly detected, before annihilating back into the vacuum. These aren't theoretical conveniences, they're real. The Casimir effect, a measurable attractive force between two uncharged metal plates placed very close together in a vacuum, is caused directly by virtual particle fluctuations, and it has been measured in laboratories. The vacuum is doing something. It has energy. The question is, how much? When physicists calculate the vacuum energy density, when they sit down with quantum field theory and add up the 0 point energies of all the quantum fields in the standard model, they get a number. A very large number. Depending on exactly how the calculation is performed and what cutoff energy you use, the predicted vacuum energy density comes out somewhere around 10 to the power of 113 joules per cubic meter, or expressed as a cosmological energy density, roughly 10 to the power of 120 times larger than the observed value of dark energy. Let me try to make 10 to the power of 120 feel real, because your brain is going to bounce off it if I don't. Imagine the observable universe, everything within about 46 billion light-years of Earth in every direction, the entire sphere of space whose light has had time to reach us since the Big Bang. That volume of space contains roughly 10 to the 80 atoms. If you took every atom in the observable universe and replaced it with an entire observable universe made of atoms, you'd have about 10 to the power of 160 atoms. Still less than the discrepancy. If you tried to write out 10 to the power of 120 in standard notation, a 1 followed by 120 zeros, it wouldn't fit on this screen. It wouldn't fit on a piece of paper the size of a football field. You'd need a strip of paper stretching from here to the moon just to write the number down. That's how wrong the prediction is. This discrepancy, theory predicting 10 to the power of 120 times too much vacuum energy, has been described by physicists as probably the worst theoretical prediction in the history of physics. That phrase appears in peer-reviewed literature. It's not hyperbole from a science journalist or an over-enthusiastic YouTuber. It's the physics community's own assessment of where their best theory stands relative to observation. Think about what that means. Quantum field theory predicts the magnetic moment of the electron, a measure of how the electron responds to magnetic fields, to an accuracy of better than 1 part in 10 billion. That's equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. The theory is, in almost every domain it touches, extraordinarily, almost impossibly precise. And then it looks at empty space and misses by 10 to the power of 120. The same theory, the same equations. Applied to the vacuum, the simplest possible physical system, literally nothing, and producing an answer that is so catastrophically, cosmically wrong that, if it were correct, you wouldn't be here to find it wrong. Something must be cancelling the vacuum energy, almost all of it, leaving just a tiny residual, the value we observe as the cosmological constant, through some mechanism that nobody has found. Various ideas have been proposed. Supersymmetry, the theoretical extension of the Standard Model that pairs every known particle with a heavier superpartner, would, in principle, cancel the vacuum energy contributions of bosons against those of fermions. If supersymmetry were exact, if every particle had a perfect superpartner of identical mass, the cancellation would be exact and the cosmological constant would be zero. But supersymmetry, if it exists at all, is broken. The partners have different masses. The cancellation is imperfect. You're left with a residual that is still far too large. String theory landscapes propose that the universe is just one of an astronomically large number of possible universes, a multiverse in which different regions have different values of the cosmological constant. Most of those universes would have cosmological constants so large that they'd expand or collapse before structure could form. We happen to live in one of the rare universes where the value is small enough for galaxies and stars and planets and observers to exist. This is an anthropic argument. We observe a small cosmological constant because only in universes with a small cosmological constant can observers exist. It's logically coherent. It's also deeply unsatisfying to most physicists because it can't be tested and provides no actual physical mechanism. Some recent work has argued that the vacuum energy doesn't actually gravitate, that the enormous quantum vacuum energy is real but doesn't couple to gravity in the way the naive calculation assumes. This is a minority position that hasn't gained broad acceptance but is actively explored. None of these approaches has solved the problem. The cosmological constant problem remains, as of April 2026, completely open. One of the greatest minds in theoretical physics, Steven Weinberg, himself a Nobel laureate who made important early contributions to thinking about the cosmological constant, described it as a problem that has resisted every approach that theorists have tried. It's not for lack of effort. The cosmological constant problem has been worked on by some of the most talented physicists in the world for decades. It has generated thousands of papers. It has influenced the direction of theoretical physics in profound ways. And the answer remains unknown. So, if the cosmological constant is the leading description of dark energy, but is so theoretically problematic, what are the alternatives? What else could dark energy be? The most developed alternative is quintessence. The name comes from the ancient Greek concept of the fifth element, the quinta essentia, the mysterious celestial substance that Aristotle believed filled the heavens beyond the four earthly elements of earth, water, fire, and air. It was the stuff of the stars, eternal and unchanging. Modern physics has borrowed the name and given it an almost opposite meaning, a dynamic, changing field that evolves over cosmic time. In the quintessence framework, dark energy is not a fixed property of empty space. It's a scalar field, something like the Higgs field, but operating at cosmological scales, that has its own energy density and evolves according to its own equations of motion. Think of it like a ball rolling slowly down a very gentle slope. The ball's position represents the field's value. As the universe ages, the field slowly changes. Its energy density isn't fixed. It can increase or decrease over cosmic time depending on the shape of the potential energy landscape the field is rolling through. This is crucial for the expiration date. A true cosmological constant, fixed, eternal, would push the universe apart forever. There's no mechanism within a constant dark energy for the reversal that produces the big crunch. But quintessence, being dynamic, could weaken over time, could lose energy, could eventually become negligible, allowing gravity to reassert itself and begin the contraction that ends in the crunch. The quintessence idea also has a potential answer, partial, imperfect, but an answer to the cosmological constant problem. If dark energy is a dynamic field slowly evolving toward zero, then the current small value isn't mysterious in the same way. It's not a coincidence or a cancellation problem. It's just where the field happens to be right now, on its slow roll toward its eventual resting value. The smallness of dark energy today is a consequence of the age of the universe. The field has been rolling for 13.8 billion years and still has a long way to go. This doesn't fully solve the problem. You still have to explain why the field starts with the right properties and why the potential has the right shape. But it's a different kind of problem, potentially more tractable than the brutal fine-tuning of the cosmological constant. And critically, if dark energy is quintessence, it should be measurable. Because quintessence changes over time, the expansion history of the universe should show subtle variations from the perfectly constant dark energy that the cosmological constant predicts. The expansion rate at different cosmic epochs should carry the fingerprint of how the quintessence field was behaving at those times. This is exactly what DESI was built to measure. And this is exactly where the March 2025 results become so electrifying. Because DESI, measuring the expansion history of the universe across 11 billion years of cosmic history, using 47 million galaxies and quasars, found hints that dark energy may not be constant, that its influence may be weakening over time, that the equation of state parameter, the number that encodes whether dark energy is a cosmological constant or something dynamic, may not be sitting exactly at the value a true cosmological constant would produce. But I'm getting ahead of the story again. Before we get to DESI and the crack in the model, there's one more thing you need to understand about what dark energy might be. Because there's an aspect of the cosmological constant, the leading description of dark energy, that is philosophically strange in a way that goes beyond the 10 to the 120 problem. Strange in a way that has its own name, the coincidence problem. Here it is. The energy density of the cosmological constant doesn't change. It's constant. That's the whole point. It's the same value today as it was 1 billion years ago, as it was 10 billion years ago, as it will be 10 billion years from now. But the energy density of matter does change. As the universe expands, the same matter is distributed across a larger volume of space. The matter density dilutes. It was much higher in the early universe and has been decreasing ever since. So in the early universe, say 1 billion years after the Big Bang, matter was enormously more dense than it is today, while dark energy had exactly the same density it has now. Dark energy was completely negligible compared to matter, a tiny perturbation, irrelevant to cosmic dynamics. In the far future, say 1 trillion years from now, matter will be diluted to almost nothing, spread across a universe so vast that the average matter density is essentially zero. Dark energy, still at the same density, will dominate almost completely. The universe will be almost entirely dark energy. Right now, at this specific moment in cosmic history, 13.8 billion years into a universe that is, in one model, 33.3 billion years old, matter and dark energy are within an order of magnitude of each other. Dark energy is dominant, but not overwhelmingly so. Matter is subdominant, but still cosmologically significant. The ratio is roughly 68% to 32%, not 99.999% to 0.001%. Why? Why do we happen to be living at exactly the cosmic moment when matter and dark energy are comparable? Not when matter completely dominated, not when dark energy completely dominates. The specific sliver of time when both are significant. The density of matter changes as the universe expands. The density of dark energy doesn't. For most of the universe's history, these two quantities have been wildly different from each other. The window of time during which they're comparable, during which an observer would measure both as significant, is cosmologically narrow. And we're in it. This is called the cosmic coincidence problem, and it's separate from the 10 to the 120 problem. Even if you accept the cosmological constant as a given, and don't worry about why it's so small, you still have to explain why it happens to be comparable to the matter density right now, in the epoch when observers exist to measure it. Some physicists accept the anthropic explanation. Observers can only exist when conditions allow for galaxies and stars and planets, which requires matter to be significant. So, of course, we observe a universe where matter matters. By definition, we couldn't exist in an epoch where it didn't. The coincidence is a selection effect. Others find that deeply unsatisfying. It feels like explaining why you won the lottery by pointing out that someone had to win. Technically correct, not illuminating. If dark energy is quintessence rather than a true cosmological constant, the coincidence problem takes a different form. In some quintessence models, called tracker models, the dark energy density automatically tracks the matter density during the matter-dominated era and only begins to dominate when certain conditions are met. The coincidence becomes less coincidental because the physics of the quintessence field naturally produces the transition at roughly the right time. This is one of the attractions of quintessence as a framework. It potentially explains the coincidence that the cosmological constant leaves mysterious. Now, there is one more candidate for dark energy that sits outside the particle physics framework entirely. It doesn't require a new particle or field. It doesn't invoke vacuum energy or scalar fields or higher dimensional landscapes. It asks a different kind of question. What if dark energy doesn't exist at all? What if what we're calling dark energy is actually a sign that general relativity, Einstein's theory of gravity, the framework within which all of modern cosmology is built, is wrong at cosmological scales? Not wrong in the solar system, where it has been tested to extraordinary precision, but wrong when applied to the universe as a whole, across distances of billions of light years, on timescales of billions of years. Modified gravity theories propose exactly this. The most developed versions modify the equations of general relativity at large scales in ways that produce an effective repulsion, something that looks like dark energy, without requiring any new energy component. The acceleration of the universe's expansion becomes a geometric effect, a consequence of gravity behaving differently than Einstein described when applied to the cosmos as a whole. The appeal is obvious. Instead of introducing a mysterious, undetectable, theoretically catastrophic new ingredient, you modify the theory of gravity. If the modification is right, You've eliminated dark energy entirely. No 10 to the power of 120 problem. No coincidence problem. Just a more complete theory of gravity. The problem is that general relativity is extraordinarily well tested. In the solar system, in binary pulsars, in gravitational wave observations, in the bending of light around massive objects, everywhere it's been tested, general relativity works perfectly. Modified gravity theories have to reproduce all of those successes, while also producing different behavior at cosmological scales. Most of the modifications that have been proposed have faced serious observational challenges. Some have been ruled out. Others survive but require careful tuning of their own. The mainstream view is that dark energy, some form of energy driving the accelerating expansion, is real, and that general relativity on large scales is broadly correct. But the mainstream view is not unanimous, and modified gravity remains an active research area. What would settle the debate? The same thing that would settle the question of whether dark energy is a cosmological constant or quintessence. Precise measurement of the expansion history of the universe across cosmic time. If dark energy is exactly constant, the cosmological constant, the expansion history has a specific shape. If dark energy evolves, quintessence, the shape is different. If it's modified gravity, the shape is different again. The differences are subtle. They require measuring the distances and recession speeds of millions of galaxies across billions of years of cosmic history. That is exactly what DESI has been doing for 5 years. That is exactly what Euclid is doing right now in orbit around the Sun. That is exactly what the Nancy Grace Roman Space Telescope, construction completed in November 2025, launch targeted for September 2026, was built to do. And the early results from DESI, announced in March 2025, showed something that nobody was quite expecting. Not a definitive answer. Science rarely delivers those on the first attempt. But a hint, a crack, a deviation from the perfectly constant dark energy that the cosmological constant predicts. A hint that dark energy might be weakening over time, that has now reached a statistical significance of up to 3.9 sigma. Not the 5 sigma threshold that physics requires before claiming a discovery, but far too large to ignore. If the hint is real, if dark energy is genuinely evolving, genuinely weakening, genuinely dynamic rather than constant, then the cosmological constant is not the complete picture. And something else is doing the driving, something that changes, something that can weaken, something that, given enough time, could weaken enough to let gravity back into the contest. And if gravity gets back into the contest, the expansion stops. And if the expansion stops, it reverses. And if it reverses, well, you know where this is going. You've known since section 1. 33.3 billion years. The receipt is real. But to understand why the hint in the DESI data is so significant, why a 3.9 sigma deviation from a constant is enough to make physicists take the expiration date seriously, you need to understand the scale of what DESI actually did. The instrument, the engineering, the 5 years of pointing 5,000 fiber optic eyes at the sky every 20 minutes, and building a map of 47 million galaxies that covers 11 billion years of cosmic history. You need to understand just how hard humanity worked to find this crack. And then you need to understand what the crack means. There's a mountain in Arizona called Kitt Peak. It sits at an elevation of about 2,100 meters in the Quinlan Mountains, southwest of Tucson, in territory that belongs to the Tohono O'odham Nation, a people who have lived in this desert landscape for thousands of years, and who call the mountain Eolegum Duag. The air up there is dry and clear and remarkably steady, the kind of atmospheric conditions that astronomers spend careers searching for. On the summit there are 24 telescopes belonging to various institutions. Most nights, most of them are pointed at something. But one of them is different from the others. The Nicholas U. Mayle telescope is a 4-meter optical telescope that has been operating on Kitt Peak since 1973. For most of its life, it was a conventional research instrument, pointing at stars, galaxies, nebulae, doing the quiet, accumulating work of observational astronomy. Then, starting around 2015, it was retrofitted with something that transformed it into one of the most ambitious scientific instruments ever built: the Dark Energy Spectroscopic Instrument, DESI. From the outside, DESI looks like a modification to an existing telescope. From the inside, it's a completely different kind of machine. At its focal plane, the point where the telescope's optics bring light to a focus, there are 5,000 tiny robots. Each one is a fiber optic positioner, a small automated arm that can swivel independently and precisely to point its fiber optic cable at a specific target in the sky. Each fiber carries light from that target, a galaxy or quasar billions of light-years away, down through the telescope and into a spectrograph, where the light is spread into its component wavelengths and recorded. 5,000 robots, 5,000 simultaneous targets. Every 20 minutes, the entire array reconfigures, each of the 5,000 positioners independently swiveling to a new target, a new galaxy, a new set of photons that have been traveling toward Earth for billions of years, and begins a new observation. The positioning precision required is extraordinary. Each fiber must point to within 1/10 of the width of a human hair of its target, consistently, repeatedly, thousands of times per night, every clear night, for 5 years. Think about what that actually means operationally. Over the course of its planned survey, DESI pointed at a new configuration of 5,000 targets roughly every 20 minutes, for perhaps 8 hours of dark sky per night, for roughly 300 usable nights per year, for 5 years. That's something on the order of millions of individual pointings, millions of spectra collected, from tens of millions of galaxies and quasars, spread across the sky and across cosmic time, their light carrying information about how fast they were receding from us at the moment the light left them, which tells you how fast the universe was expanding at that moment, which tells you what dark energy was doing then. That's the logic of the whole enterprise. If you know how fast the universe was expanding at many different moments in its history, 3 billion years ago, 6 billion years ago, 9 billion years ago, you can construct the expansion history. And the expansion history carries the fingerprint of dark energy. A cosmological constant produces one specific expansion history. Quintessence produces a slightly different one. Modified gravity produces another. The differences are subtle. We're talking about percent-level deviations in the expansion rate at different cosmic epochs. But with enough galaxies, measured precisely enough, those differences become detectable. DESI was built to detect them, and it did it using a technique called baryon acoustic oscillations, BAO. It's a beautiful piece of physics, and it's worth understanding, because it's the core of what DESI measured, and why those measurements carry the weight they do. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma, a soup of protons, electrons, and photons, all tightly coupled together, bouncing off each other, unable to move independently. Through this plasma, pressure waves propagated, sound waves in a very real sense, though at frequencies far below anything a human ear could detect. These acoustic waves traveled outward from regions of slight overdensity, carrying energy and matter with them. Then, 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The plasma became a neutral gas. The photons, freed from their coupling to matter, streamed away as the cosmic microwave background. And the sound waves, without a medium to propagate through, froze in place. They left a physical imprint. A preferred scale, the distance those pressure waves had traveled in 380,000 years, roughly 490 million light years, is baked into the distribution of matter in the universe. Galaxies are slightly more likely to be separated by that specific distance than by distances slightly larger or smaller. It's a statistical signal in the galaxy distribution, subtle but detectable if you have enough galaxies. That preferred separation distance is the Baryon Acoustic Oscillation Scale. It's a standard ruler, a known physical length that you can measure at different distances from Earth, and therefore at different points in cosmic history, and use to track how the universe has expanded. If the ruler appears larger than expected at a given distance, the universe expanded more between then and now than you predicted. If it appears smaller, the universe expanded less. By measuring the apparent size of the BAO scale in galaxy surveys at different redshifts, different distances corresponding to different cosmic epochs, you can reconstruct the expansion history with exquisite precision. And that's exactly what DESI has been doing. Using 47 million galaxies and quasars as data points, measuring the BAO scale at different cosmic epochs, building a map of how the universe has expanded over the past 11 billion years, and then asking, does this expansion history match the prediction of a universe with a constant dark energy, a cosmological constant? Or does it show deviations that suggest dark energy has been changing? The answer, from the first 3 years of DESI data released in March 2025, was it might be showing deviations. Let's be precise about what the DSI results actually said, because this is a place where the difference between hint and discovery matters enormously, and it's easy to overstate or understate what was found. DSI's data, taken alone, is consistent with the standard model. Lambda CDM, cosmological constant. The DSI-BAO measurements by themselves don't rule out a constant dark energy. This is important. DSI alone isn't claiming to have overthrown the cosmological constant. But cosmological measurements are never analyzed in isolation. You combine different probes, BAO, supernovae, the CMB, because each one constrains different combinations of cosmological parameters, and the combination is much more powerful than any single probe alone. When the DSI team combined their BAO measurements with supernova data, specifically the Type 1a supernova datasets that have been accumulated since the original 1998 discovery, and with CMB measurements from the Planck satellite and the Atacama Cosmology Telescope, the picture shifted. The combined dataset showed hints of a deviation from a cosmological constant. In the technical language of cosmology, dark energy's behavior is characterized by an equation of state parameter called W. If dark energy is a true cosmological constant, W equals exactly -1. Always, everywhere, at every point in cosmic history. The number -1 is the cosmological constant's signature. The DSI combined results, depending on which supernova dataset was included in the combination, showed W deviating from -1 at a statistical significance ranging from 2.5 sigma to 3.9 sigma. Specifically, the data preferred a dark energy that was stronger in the early universe and is weakening over time. Not a static, eternal cosmological constant. Something dynamic, something evolving, something that is, right now, losing its grip on the universe's expansion. 3.9 sigma sounds impressive. It is impressive. In everyday terms, a 3.9 sigma deviation from a null result would be front-page news in almost any other field. In particle physics, 5 sigma is the convention for claiming a discovery, chosen specifically because 5 sigma events occur by random chance only about 1 in 3.5 million times. A 3.9 sigma deviation occurs by chance roughly 1 in 10,000 times. That's not negligible. That's not easily dismissed. But it's not 5 sigma. And in physics, that difference matters. Why 5 sigma? Because the history of particle physics and cosmology is littered with 3 sigma and 4 sigma signals that turned out to be statistical fluctuations, systematic errors, or analysis artifacts. The 5 sigma convention exists precisely because the field has been burned before. Hints that looked compelling at 3 sigma and then disappeared when more data came in. Signals that seemed real and turned out to be instrumental artifacts. Science learned, the hard way, to be skeptical of anything below 5 sigma. Not dismissive, skeptical. Attentive, but cautious. The Chinese Academy of Sciences researchers from the DESI collaboration pushed the significance further in their analysis. They reported that the equation of state for dark energy evolves over time at 4.3 sigma confidence, excluding Einstein's cosmological constant. Still below 5 sigma, still not a confirmed discovery, but stronger. So where does that leave us? In a place that is genuinely, productively uncomfortable. The data is saying something. The question is whether what it's saying is real signal or noise. Mustafa Ishak Boushaki is a professor of physics at the University of Texas at Dallas and co-chair of the DESI working group that interprets the collaboration's cosmological survey data. He's been one of the central scientific figures in processing and communicating what DESI has found. When the March 2025 results were announced at the American Physical Society's Global Physics Summit in Anaheim, California, Ishak Boushaki was one of the lead voices explaining what the collaboration had found. His framing was careful. He acknowledged the hints. He acknowledged their significance. He also acknowledged that the full DESI dataset, the complete 5 years of observations that were still being collected at the time, would be needed to say anything definitive. The hints could strengthen into a discovery. they could also fade. That's what the data would tell them. That full 5-year dataset was completed on April 14, 2026. The morning after DESI's final scheduled observation, the collaboration marked the milestone. The instrument had surpassed its original goals in almost every way. More galaxies measured, more area covered, better precision than planned. The complete dataset has now measured cosmological data for 6 times as many galaxies and quasars as all previous surveys combined. The first dark energy results from the complete 5-year survey are expected in 2027. That result, whatever it shows, will be one of the most consequential measurements in the history of cosmology. If the hint of evolving dark energy grows with more data and crosses the 5 sigma threshold, the cosmological constant is ruled out as the complete picture. A century of physics built around Einstein's lambda will need revision. Quintessence, or something like it, becomes the leading framework. And the expiration date, the big crunch, the 33.3 billion years, becomes far more credible. If the hint fades, if the 3.9 sigma deviation shrinks towards 0 with more data, then the cosmological constant survives. Dark energy stays constant. The universe expands forever. No crunch. The receipt turns out to have been misread. We genuinely don't know which way it will go. That's not a rhetorical hedge. It's the actual state of the science as of April 2026. But the DESI results aren't the only crack in the standard model. There's another one. Deeper, stranger, and in some ways more disturbing. Because while the DESI deviation from the cosmological constant is a hint that might fade, the second crack has been growing for over a decade and shows no sign of going away. It's called the Hubble tension. The Hubble constant, named for Edwin Hubble, who first measured the expansion of the universe in 1929, is the number that describes how fast the universe is currently expanding. It's usually expressed in units of kilometers per second per megaparsec. For every megaparsec of distance between 2 objects, those objects are receding from each other at the Hubble constant in kilometers per second. The current best estimates put it somewhere between 67 and 73 kilometers per second per megaparsec. That range, 67 to 73, sounds like a small uncertainty. It's not. It's a crisis. Here's the problem. There are 2 fundamentally different ways to measure the Hubble constant. The first is from the early universe, specifically from the cosmic microwave background. The Planck satellite measured the CMB with extraordinary precision and derived a Hubble constant of about 67.4 kilometers per second per megaparsec. This measurement is based on the physics of the early universe, the acoustic oscillations in the plasma before recombination, the specific pattern of hot and cold spots in the CMB, and is considered extremely reliable. The second method is from the late universe, from measuring distances and recession speeds of nearby galaxies using a cosmic distance ladder that starts with Cepheid variable stars and extends to Type 1a supernovae. This method, championed largely by Adam Rees, the same Adam Rees who shared the 2011 Nobel Prize for discovering the accelerating expansion, gives a Hubble constant of about 73 kilometers per second per megaparsec. 67.4 versus 73. Those numbers do not agree. And they're getting further apart as both measurements improve. In the early years of the discrepancy, it was plausible to think that one or both measurements had systematic errors that would be identified and corrected. As the measurements got more precise, the tension would likely resolve itself. Measurement error would explain the gap. That's not what happened. Both measurements have been refined, cross-checked, and independently replicated. The error bars have shrunk. The central values haven't converged. The tension has grown. At the Tensions in Cosmology 2025 conference held in Corfu, Greece, attended by more than 130 researchers gathered specifically to assess the cracks in the standard cosmological model, the Hubble tension was reported to have exceeded 6 sigma. 6 sigma. The standard for a discovery in physics is 5 sigma, an event that would occur by random chance 1 in 3.5 million times. 6 sigma corresponds to odds of roughly 1 in a billion. The discrepancy between the early universe and late universe measurements of the Hubble constant is now so statistically robust that if it were any other kind of result, a new particle, a new astronomical phenomenon, it would have been declared a confirmed discovery years ago. It hasn't been declared a discovery because nobody knows what it's a discovery of. The two measurements are both right, or at least no systematic error has been found in either that would explain the gap. Which means the standard model of cosmology, lambda CDM, is producing predictions that are inconsistent with observations. Something is missing from the model. Dark energy evolution is one of the proposed explanations. If dark energy is not a cosmological constant, if it changes over time, then the expansion history of the universe is different from what the standard model predicts. The CMB-based measurement of the Hubble constant is calibrated against a specific cosmological model. If that model is wrong because dark energy evolves differently than assumed, the inferred Hubble constant would be wrong too, in a direction that could explain the tension. A March 2026 paper, published in the Astrophysical Journal, laid this out explicitly. Using DESI 2025 data, combined with CMB and supernova measurements, the authors found 3 key results. First, the Hubble tension persists across all models they tested. Second, there is compelling evidence for dynamical dark energy that evolves over time, with the early universe preferring one phase and the late universe another. Third, the full dataset suggests a late-time interaction between dark energy and matter. Their conclusion: dark energy evolves with cosmic time, challenging the cosmological constant paradigm. That's a significant statement from a peer-reviewed paper in a major journal. Not a fringe claim, not a sensational preprint, a careful analysis of the best available data. But the Hubble tension has another possible explanation that is even more radical. What if the problem isn't with dark energy, but with the early universe? Some theorists have proposed that there was a period of early dark energy, a brief burst of dark energy-like behavior in the first moments before recombination, that changed the sound horizon, the physical scale of the CMB acoustic oscillations, and therefore changed the calibration of the CMB-based Hubble constant. If you add early dark energy to the model, the CMB measurement shifts upward toward the late universe value, and the tension partially resolves. But early dark energy has its own problems. It doesn't fully resolve the tension in most models. It introduces new tensions elsewhere in the data. It requires new physics, a new energy component in the early universe, without a clear theoretical motivation. No single explanation has won. As the Tensions in Cosmology 2025 conference report concluded, no single theory or modification could resolve the Hubble tension, and any solution will likely involve modifications to both early and late universe physics. The standard model has 2 cracks. The DESI dark energy evolution hint, which might be temporary, and the Hubble tension, which has been growing for a decade and shows no sign of resolution. Two separate, independent anomalies pointing to the same conclusion. Something in our picture of the universe is wrong. Now, step back and look at the situation from a distance. In 2025 and 2026, cosmology is in a state that feels genuinely like a turning point. Not a crisis in the sense of panic or confusion. The standard model still works extraordinarily well for most purposes, still reproduces the large-scale structure of the universe, still matches the CMB to extraordinary precision. But at the edges, in the precision measurements, in the detailed comparisons between different cosmic epochs, cracks are appearing. The most important instrument in the effort to understand these cracks, DESI, has just completed its planned survey. On the night of April 14, 2026, its 5,000 fiber-optic eyes locked onto a patch of sky near the Little Dipper for one of the last times in the originally planned mission. Photons arrived. Spectra were recorded. Data was added to the most comprehensive cosmic map ever assembled. And when the sun rose, the collaboration marked the completion of something historic. 5 years. 47 million galaxies, 6 times more data than all previous surveys combined. Finished ahead of schedule and with more observations than planned. The full dataset is now being processed. The analysis pipelines that will extract the definitive dark energy measurements are running. The results are expected in 2027. What will those results show? Nobody knows. Not the scientists who built DESI, not the theorists who developed the models, not the astronomers who spent 5 years collecting the data. The answer is in the dataset. It hasn't been extracted yet. But here's what we do know. The hints from the first 3 years pointed in a specific direction. Dark energy may be weakening. And if dark energy is weakening, if the force that has been pushing the universe apart for 5 billion years is losing its grip, then the universe has a future that looks very different from the endless, cold expansion that the cosmological constant would produce. It has a future that ends. And that future was calculated, specifically and explicitly, using the DESI data and the dark energy survey data together, by a physicist at Cornell University named Henry Tai and his collaborators. The calculation produced a number, 33.3 billion years. We've been living with that number since Section 1. Now it's time to understand exactly how it was derived, what the end it predicts actually looks like, and, perhaps most importantly, how certain we can be that it's real. Because it's time to read the receipt all the way to the bottom. Let's read the receipt, not the summary, not the headline, the whole thing, line by line, from where we are now to the last moment of everything. Because Henry Tai's calculation isn't just a number, it's a narrative, a sequence of events, each one following from the last with the cold logic of physics. Each one more extreme than the one before, building towards something that has no precedent in the history of the universe except the event that started it. But before we walk through the timeline, you need to understand where the number comes from. Because 33.3 billion years isn't a guess. It isn't a philosophical estimate. It's the output of a specific physical model, built on specific data, making specific assumptions that can be tested. Understanding those assumptions is what lets you hold the number with the right combination of seriousness and appropriate skepticism. Henry Tai is the Horace White Professor of Physics Emeritus at Cornell University. He's a theoretical physicist, a string theorist by training, who has spent his career thinking about the deep structure of physical reality. In 2025, he and collaborators from Cornell, Shanghai Jiao Tong University, and other institutions turned their attention to the DESI results and the dark energy survey data and asked a specific question. If dark energy is not a true cosmological constant, if it's dynamic, changing, weakening over time, as the DESI hints suggest, what is the simplest physical model that fits the data? And what does that model predict about the future of the universe? The model they constructed starts with a key insight. The DESI data hints that dark energy's behavior is changing over cosmic time. One way to produce that behavior, mathematically, is to assume that what we're calling dark energy is actually two things. First, an underlying cosmological constant that is negative lambda. A constant energy density that, rather than pushing things apart, would eventually pull things together, producing collapse. Second, a temporary additional energy component, a scalar field, a quintessence-like contribution that is currently positive and large enough to overwhelm the negative cosmological constant, producing the observed acceleration. Right now, the positive scalar field component dominates. The universe accelerates. Dark energy appears to be pushing everything apart, just as the cosmological constant model predicts. But the scalar field changes over time. It slowly decays. Its energy density decreases, and, as it weakens, the underlying negative cosmological constant, always there, always negative, always pulling toward collapse, becomes progressively less overwhelmed. Eventually, the scalar field decays enough that the negative lambda wins. The net dark energy flips sign. The repulsive force that has been driving the acceleration becomes an attractive force. The expansion doesn't just slow, it stops, and then it reverses. This model fits the DESI data well. It provides a simple mechanism for the evolving dark energy that the data hints at. It makes a concrete prediction about the future, and that prediction, when you plug in the numbers from the data, produces a total cosmic lifespan of approximately 33.3 billion years. Tai described his own reaction to the result with the directness of a physicist who has spent a career thinking about big numbers. For the last 20 years, he said, people believed that the cosmological constant is positive and the universe will expand forever. The new data seem to indicate that the cosmological constant is negative and that the universe will end in a big crunch. And then, critically, people have said before that if the cosmological constant is negative, then the universe will collapse eventually. That's not new. However, here the model tells you when the universe collapses and how it collapses. When and how. A specific timeline, a specific mechanism. Let's follow that timeline from now to the end. Where we are, 13.8 billion years after the Big Bang. The universe is currently in what cosmologists call the dark energy-dominated era. For the past 5 billion years, dark energy has been winning the tug-of-war against gravity, and the expansion of space has been accelerating. Galaxies are receding from each other at increasing speeds. The observable universe, the sphere of space whose light has had time to reach us, is roughly 93 billion light-years in diameter, a number that seems paradoxical given the 13.8 billion-year age of the universe, but results from the fact that space itself has been expanding during the time the light was traveling.
At this moment, the universe is extraordinary in its richness. There are an estimated 2 trillion galaxies in the observable universe. Each galaxy contains hundreds of billions to trillions of stars. Many of those stars host planetary systems. The universe is still actively forming stars. New stars are being born right now in molecular clouds scattered across countless galaxies. It's a universe at something like its peak of complexity. Not its peak of star formation, that was billions of years ago, but its peak of accumulated structure, accumulated complexity, accumulated possibility. This is the universe at 13.8 billion years. Busy, complex, rich. In the Tai model, This phase continues for approximately another 11 billion years. 11 billion years from now, the expansion peaks. Over the next several billion years, to the outside observer, if any existed across cosmic distances, the universe would look broadly similar to today. Galaxies still forming new stars, though at a declining rate. The Sun, long dead by this point, it exhausts its hydrogen fuel in roughly 5 billion years, expands into a red giant that engulfs Mercury, Venus, and likely Earth, then sheds its outer layers and settles into a white dwarf, cooling slowly over billions of years. Whatever becomes of life on Earth, or whatever emerged from Earth's ruins or wherever else life exists in the universe, has had billions of years to develop by this point. But quietly, invisibly, something is changing in the dark energy. In the TIE model, the scalar field component of dark energy is slowly decaying. Its energy density is slowly dropping. The positive contribution that has been overwhelming the underlying negative cosmological constant is weakening fraction by fraction over billions of years. The net dark energy, currently strongly positive, strongly repulsive, is declining. The expansion rate of the universe, which had been increasing, begins to level off. The acceleration slows. For the first time in roughly 16 billion years, the universe is no longer accelerating. The expansion continues, but at a constant rate. Then the rate begins to decrease. Gravity is entering the contest again. In approximately 11 billion years from now, about 24.8 billion years after the Big Bang, the expansion rate reaches zero. The universe is as large as it will ever be, an enormous, cold, ancient cosmos, most of its stars burned out, most of its galaxies having merged or been flung apart, sitting at its maximum extent. A moment of cosmic stillness. And then it begins to fall. The first phase of collapse, billions of years of slow contraction. The reversal is imperceptible at first. The distances between galaxy clusters, groups of galaxies so far apart that dark energy had been pushing them apart at increasing speeds, begin incredibly slowly to decrease. Not because the galaxies are moving toward each other, because the space between them is contracting. The expansion of space, which has been the dominant feature of the universe for 24.8 billion years, goes into reverse. The recession speeds of distant objects, which astronomers measure as redshift, the stretching of light toward longer wavelengths, begin to decrease. Objects that were moving away from us in the familiar cosmological sense begin to blue shift. Their light is shifting toward shorter, bluer wavelengths as the space between us and them contracts. Over millions of years, then billions. The cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space at a temperature of 2.725 degrees above absolute zero today, begins to warm. During the expansion, this background radiation was being stretched and cooled as space grew. Now, as space contracts, it's being compressed and heated. The wavelengths of the CMB photons shorten. Their energy increases. The background temperature of the universe, which has been dropping for 24.8 billion years, begins to rise. Slowly, at first. In the early stages of the contraction, the universe looks recognizable. Most stars have burned out, but stellar remnants, white dwarfs, neutron stars, black holes, still exist. The dark matter halos that surround galaxies still hold structure in place. The large-scale architecture of the universe, the cosmic web of filaments and voids, is still there, though compressed and distorted by the contraction. Galaxy clusters that had been moving apart at enormous speeds are now drifting back toward each other. The voids between them, vast empty regions of space, hundreds of millions of light-years across, are shrinking. The universe is folding back on itself, slowly, with the gravity of everything pulling toward everything else. The acceleration of collapse. Things get violent. As the contraction continues and space grows smaller, matter becomes more densely concentrated. Gravity, which falls off with distance and had been losing the battle against dark energy's repulsion, grows stronger as objects move closer together. The collapse accelerates. Galaxy clusters begin to merge. Not in the slow, gentle way that galaxies within clusters have been merging throughout cosmic history, but faster, more energetically, as the contraction squeezes everything closer together. The distances that had been expanding for 24 billion years compress in a fraction of that time, because gravitational collapse accelerates as density increases. The background temperature of the universe keeps rising. The CMB, compressed by the contraction, warms from its current cryogenic value toward temperatures that are first cool, then comfortable, then hot. When the CMB temperature reaches the temperature of a star's surface, a few thousand degrees, something remarkable and terrible happens. Stars, which have always existed in an environment much cooler than their interiors, suddenly find themselves surrounded by radiation as hot as their own surfaces. They can no longer radiate energy outward. The temperature gradient that drives stellar energy loss disappears. Stars begin to disintegrate. Their outer layers, no longer able to shed heat into a cooler environment, bloat and disperse. Whatever stellar remnants exist at this point, white dwarfs, the fading embers of 100 trillion dead stars, are evaporated by the rising cosmic temperature. The universe is becoming hostile to structure at the stellar scale. The final phase, everything at once. As the contraction approaches its climax, the pace of change becomes breathtaking on any timescale. What took billions of years in the expansion, the gradual thinning of matter, the slow cooling of the background radiation, now happens in reverse at accelerating speed. The universe is in freefall. The background temperature climbs through tens of thousands of degrees, through millions. The thermal radiation filling all of space becomes energetic enough to destroy atoms. Electrons are stripped from nuclei. Matter reverts to plasma, the same state it was in for the first 380,000 years after the Big Bang. But the conditions are no longer gently declining as they were then. They're escalating. At temperatures of billions of degrees, atomic nuclei begin to disintegrate. Protons and neutrons, fused together in nuclear reactions inside stars over trillions of years of cosmic history, are blasted apart by the rising thermal energy. The complex nuclear structures that make up every element heavier than hydrogen, every atom of carbon, oxygen, iron, gold, every element that exists only because stars lived and died and seeded space with their ashes, are undone in the final moments. Matter reverts to its most fundamental components, quarks and gluons. The hadron epoch of the early universe reversed. The geometry of space itself, which has been the arena within which all of this has played out, is collapsing. There is no outside to the universe where you could watch this happen. Every point in space is experiencing the same conditions simultaneously. There is no safe corner, no region less affected than another. The collapse is universal, total, symmetric. And then, approximately 20 billion years from now, 33.3 billion years after the Big Bang, according to the time model, everything that exists, everything that has ever existed, every particle of matter and every quantum of energy occupies a single point of infinite density. The Big Crunch. It's the temporal mirror image of the Big Bang, a singularity, a boundary of space-time. Physics, as we know it, breaks down at this point. The equations of general relativity produce infinities, which is their way of telling you that something beyond general relativity is needed to describe what happens here. Whether the crunch is truly a final end, or whether quantum gravity effects produce a bounce, a new Big Bang, a new universe,
a new 33.3 billion year story beginning again, is a question that current physics cannot answer. But in the time model, the calculation ends at the crunch. That's the lifespan. That's the expiration date. 33.3 billion years total. 13.8 billion already elapsed. Roughly 19.5 billion remaining. Let's make those remaining years feel real, because they're not all the same. In the next 5 billion years, well within the expansion phase, business essentially as usual except the sun dies, the Earth will be swallowed by the expanding sun. The solar system will be reorganized around a cooling white dwarf, and whatever life has managed to do with 5 billion more years of cosmic time will have to have found somewhere else to be. The universe will still be rich with stars, still forming new ones in the youngest galaxies. In the next 4 to 5 billion years after that, the Milky Way and Andromeda complete their merger, a collision that has already been confirmed by astronomers using Hubble Space Telescope observations of Andromeda's proper motion. The two spiral galaxies will interact, their stars mostly passing through each other, but the whole structure reshaping into a large elliptical galaxy. Astronomers already have a name for the result: Milkomeda. The night sky over any remaining planet in the merged galaxy will be spectacular in ways we can't fully imagine. Stars crowded densely, gravitational interactions constant, the galactic center dramatically more prominent. In the following billions of years, the universe continues cooling and dimming. Stars burn out faster than new ones form. The stellar population ages. Galaxy clusters outside our local group, already being pushed away by dark energy today, will have crossed our cosmic horizon and vanished from observability entirely, their light unable to reach us in a universe whose expansion had, in the Standard Model, been accelerating. In the TIE model, this process goes into partial reverse, as the expansion slows and eventually stops. Some of those lost galaxies become reachable again, as the contraction brings them back within causal contact. In the epoch roughly 10 to 11 billion years from now, the expansion stops. The universe sits at its maximum size. Whatever intelligence exists at that point, and we have absolutely no way to say whether anything does, will be observing a universe in a moment of profound transition. The evidence of what's coming would be subtle at first. Blue shifts where there had always been red shifts, the cosmic background radiation ticking upward in temperature, fraction of a degree by fraction of a degree. And then the long fall inward. Now, two things need to be said clearly about this timeline. The first is about certainty. The TIE model is a model. It's built on the DESI and DES data, which, as of March 2025, showed hints of evolving dark energy at up to 3.9 sigma, significant but below the 5 sigma discovery threshold. The model also involves a specific assumption about the structure of dark energy, a negative underlying cosmological constant plus a decaying scalar field, that is theoretically motivated but not uniquely supported by the data. Other models can also produce evolving dark energy without predicting a big crunch. The 33.3 billion year figure is the output of one specific model fit to the available data. If the full DESI 5-year dataset, when analyzed in 2027, shows that the hint of evolving dark energy was a statistical fluctuation, that dark energy is actually constant after all, the TIE model's prediction goes away. The cosmological constant is restored.
The universe expands forever. The receipt was misread. If the hint strengthens to 5 sigma or beyond, if the full dataset confirms that dark energy is genuinely weakening, then the Big Crunch becomes a serious scientific prediction rather than a compelling model. Not certain even then, the specific form of dark energy evolution needed to produce the crunch versus other forms that produce different outcomes will require further precision. But serious. The kind of serious that gets written into textbooks. The second thing that needs to be said is about scale. Even if the time model is exactly right, even if the universe ends in a big crunch in precisely 33.3 billion years, the remaining 19.5 billion years is a span of time so vast that it makes all of human history look like the blink of an eye. Complex life has existed on Earth for about 600 million years. The time from now to the maximum expansion of the universe, 11 billion years, is roughly 18 times the entire history of complex life on our planet. The time from the maximum expansion to the final crunch, another 9 billion years, is 15 times more. The universe is not in imminent danger. The receipt has a due date. That due date is not tomorrow. But it is a date. And something profound happens to your relationship with the cosmos when you move from the universe is eternal to the universe has a lifespan. When the infinite becomes finite. When the permanent becomes temporary. Think about how human cultures have always related to nature. Mountains feel permanent. Oceans feel permanent. Stars feel permanent. The entire human intuition about the cosmos, encoded in every religion, every philosophy, every mythology, is built on the assumption that the backdrop is eternal. That whatever happens to individuals and civilizations and species, the stage on which everything plays out is forever. That assumption is gone now. Not destroyed. We don't know yet whether the time model is right, but it's no longer a certainty. It's a hypothesis. The stage might have an end. The backdrop might be temporary. The universe itself might be mortal. What do you do with that? The honest answer is that we don't entirely know yet. Humanity has been living with the possibility of cosmic mortality for only a few months, since the TIE result was published and received wide attention. The philosophical implications haven't fully propagated through human thought. We haven't had time to absorb it. But there's one thing that seems clear, sitting with it. The fact that we know, or might know, or are beginning to be able to know, is itself remarkable. A species that has existed for 300,000 years on a planet that has existed for 4.5 billion years, in a universe that has existed for 13.8 billion years, has built instruments sensitive enough to read the universe's energy content across 11 billion years of history, run the numbers through physical models, and produced a specific prediction about when everything ends. We found the receipt in an Arizona desert, with 5,000 fiber optic robots pointing at galaxies one by one. That's either a coincidence so staggering it defies belief, or it's what it looks like when a species is at exactly the right stage of development to begin reading the universe's deepest messages. We might be that species at exactly that moment. But might is doing a lot of work there, because the DESI result is not confirmed. The TIE model is not proven. The receipt might be wrong.
And in the next few years, as DESI's full 5-year dataset is analysed, as Euclid's survey deepens, as the Nancy Grace Roman Space Telescope launches and begins its sweeping infrared survey of hundreds of millions of galaxies, we're going to find out. The instruments that will tell us whether the clock is real are either already built, already launched, or sitting in a clean room in Maryland being prepared for a launch window in the fall of 2026. The most consequential measurements in the history of cosmology are either already happening or about to begin. That's where we're going next.
On the night of April 14th, 2026, a telescope in the Arizona desert did something for the last time. The 5,000 fiber optic eyes of the dark energy spectroscopic instrument swiveled onto a patch of sky near the Little Dipper. Every 20 minutes, they locked onto new targets: distant galaxies, ancient quasars, pinpricks of light that had been traveling toward Earth for billions of years, gathered their photons and fed them into spectrographs that spread the light into its component wavelengths and recorded what they found. When the sun rose over the Quinlan Mountains, the collaboration marked the completion of something that had taken 5 years, more than 900 researchers, over 70 institutions, and an engineering effort of extraordinary ambition. DESI's originally planned survey was done. The 5-year mission had mapped more than 47 million galaxies and quasars. It had measured cosmological data for 6 times as many objects as all previous surveys combined. It had tracked dark energy's influence across 11 billion years of cosmic history. It had finished ahead of schedule and with more data than planned. And it had produced hints, tantalizing, statistically significant, not yet conclusive, that dark energy might be changing, that the cosmological constant might not be constant, that the expiration date on the universe might be real. Now the collaboration is processing the full dataset, running the analysis pipelines, combining the 5 years of observations into the most comprehensive picture of dark energy's behavior ever assembled. And in 2027, the first dark energy results from the complete 5-year survey are expected in 2027. The answer will come. But DESI isn't working alone. Right now, in the months and years ahead, a fleet of instruments is either already operating, already built, or being prepared for launch. Each one designed to attack the dark energy problem from a different angle. Each one capable of producing measurements that could confirm, challenge, or completely transform our understanding of what the universe is made of and where it's going. This is the moment. Not in a vague, indefinite, science will figure it out someday sense. In a specific, concrete, instrument-by-instrument sense. The measurements that will tell us whether the universe has an expiration date are either happening right now or about to begin. We are living through the experimental window that will answer one of the deepest questions ever posed. Let's go through the instruments one by one, not as a list, but as a story, because each one has its own character, its own approach, its own piece of the puzzle it was built to contribute. DESI, the map that keeps growing. Even though DESI has completed its originally planned survey, it isn't finished. Because of the hints of evolving dark energy in the first 3 years of data, hints that demanded more investigation, the collaboration decided to continue observations beyond the original plan. DESI will keep running through 2028, extending its map to cover more of the sky, adding more galaxies, refining the measurements of dark energy's behavior at different cosmic epochs. The full 5-year dataset is already being processed. Several analysis papers are planned for release later in 2026, covering the structure and evolution of the universe from different angles.
And then, in 2027, the main event, the first dark energy results from the complete survey. That result will be the most important single measurement in cosmology since the original 1998 discovery of the accelerating expansion. Here's why. The DESI 5-year dataset will contain something like twice the statistical power of the 3-year dataset that produced the 3.9 sigma hint of evolving dark energy. If the hint is real, if dark energy is genuinely evolving and the signal is in the data, the 5-year analysis should push that significance well above 5 sigma. The hint becomes a discovery. If the hint is not real, if it was a statistical fluctuation or a systematic effect in the supernova datasets used in the combination, the 5-year analysis will show the significance dropping back towards zero. The cosmological constant survives. The receipt was wrong. Either outcome is scientifically extraordinary. A confirmed detection of evolving dark energy would be among the greatest discoveries in the history of physics, overturning a century of cosmological assumption and opening an entirely new era of investigation into what dark energy actually is. A null result, confirming that the cosmological constant is correct, would be deeply reassuring in some ways and deeply frustrating in others. It would mean the 10 to the power of 120 problem remains, and we have no new experimental lever to pull. But we won't have to wait for the 2027 result in total darkness, because another instrument is already providing its own independent window onto dark energy. ESA Euclid, the Dark Universe Detective in Orbit. On July 1, 2023, a Falcon 9 rocket lifted off from Cape Canaveral, carrying one of the most ambitious space science missions ever flown. The European Space Agency's Euclid satellite, named after the ancient Greek mathematician who founded geometry, rode to its destination at the Sun-Earth second Lagrange point, a gravitationally stable position about 1 million miles from Earth in the direction away from the Sun, where it joins the James Webb Space Telescope in a privileged vantage point for observing the cosmos. Euclid began regular science operations on February 14, 2024. Its mission: to map the geometry of the dark universe. To understand dark energy and dark matter not from a single vantage point in time, but across the full sweep of cosmic history, out to a redshift of about 2, which corresponds to looking back roughly 10 billion years. The scale of Euclid's ambition is matched by the scale of its technical capability. The satellite carries 2 instruments: a visible light imager with a field of view covering about 0.57 square degrees, roughly 3 times the area of the full moon, and a near-infrared spectrometer and photometer. Over the course of its planned 6-year mission, Euclid will survey 15,000 square degrees of the extragalactic sky, about a third of the entire sky, imaging more than 1 billion galaxies and obtaining spectra for tens of millions. 1 billion galaxies. The number is almost incomprehensible until you think about what it enables. Euclid measures dark energy through 2 complementary techniques. The first is weak gravitational lensing, the same technique we encountered in the dark matter video, applied here to map dark energy's influence on the distribution of matter. As light from distant galaxies passes through the universe, dark matter and dark energy both affect how that light is deflected and distorted. By measuring the statistical patterns of distortion in the shapes of 1 billion galaxies, Euclid can reconstruct the distribution of dark energy across cosmic time with extraordinary precision. The second technique is galaxy clustering, measuring how galaxies are distributed in 3-dimensional space, specifically the baryon acoustic oscillation scale, the same cosmic ruler that DESI uses. Euclid's BAO measurements from 1 billion galaxies in space rather than 47 million from the ground will provide an independent check on everything DESI has found. In March 2025, Euclid released its first science data, the Q1 dataset, covering about 63 square degrees of sky, 7 times larger than the earlier early release observations. In just 1 week of scanning, Euclid observed 26 million galaxies, the most distant of which had its light traveling for about 10.5 billion years to reach the detector. 1 week, 26 million galaxies. The scale of the instrument's productivity is staggering. The Euclid Consortium described the Q1 release as a first glimpse of the cosmological survey, illustrative of what will be extensively analyzed to map the large-scale structure of the universe across cosmic time. The full cosmological results, the ones that will place percent-level constraints on the dark energy equation of state, will emerge progressively as the survey deepens and the datasets are analyzed. Here's what makes Euclid particularly powerful in the context of our story. DESI's hints of evolving dark energy came primarily from combining its BAO measurements with supernova data. Different supernova datasets gave slightly different levels of significance. The hint ranged from 2.5 to 3.9 sigma, depending on which compilation was used. There are ongoing debates in the community about systematic effects in the supernova data, about how different supernova samples should be standardized and combined. Euclid's weak lensing measurements don't depend on supernovae at all. They probe dark energy's influence through a completely independent physical effect. If Euclid's weak lensing results are consistent with a cosmological constant, that's important information. If they show the same kind of deviation that DESI's combined analysis showed, dark energy evolving over time, that's an independent confirmation from a different instrument using different physics. 2 independent signals pointing the same way are much harder to dismiss than one. Euclid's first full cosmological results, the ones that will genuinely start to constrain the equation of state, are expected to appear over the next few years as the survey deepens. The Nancy Grace Roman Space Telescope, built to settle the question. In a clean room at NASA's Goddard Space Flight Center in Greenbelt, Maryland, on November 25, 2025, technicians joined the 2 major segments of the Nancy Grace Roman Space Telescope, the inner portion containing the instruments and the outer portion containing the structure and hardware, completing the observatory's assembly. The largest science instrument NASA has ever built was done. Roman's namesake is Dr. Nancy Grace Roman, NASA's first chief of astronomy, the woman who paved the way for space-based astronomy and who is sometimes called the mother of the Hubble Space Telescope. She obtained her doctorate in astronomy from the University of Chicago in 1949, when women in science faced systematic and often explicit exclusion. She spent her career breaking down those barriers and making cosmic vistas accessible. The telescope that bears her name will, in the assessment of its science team, transform virtually every branch of astronomy. But for the purposes of our story, what matters about Roman is this: it was designed from the beginning to settle the dark energy question. Not to investigate dark energy, to settle it. The instrument's specifications were built around that goal. Roman has a 2.4-meter primary mirror, the same size as the Hubble Space Telescope, but with a field of view more than 100 times wider. Where Hubble sees a tiny patch of sky, Roman sees a vast panorama. Where Hubble might observe a few hundred galaxies in a long exposure, Roman captures hundreds of thousands.
The Wide Field instrument at Roman's Halt is a 300 megapixel camera optimized for infrared light. Light with wavelengths longer than visible, which is what you need to observe the most distant, most redshifted galaxies in the universe. Roman will attack the dark energy problem with 3 independent techniques simultaneously. The first is weak gravitational lensing, the same technique as Euclid, applied across a wide infrared survey of hundreds of millions of galaxies. Roman's wide field and sharp infrared vision make it extraordinarily powerful for this kind of measurement. By precisely measuring the shapes of hundreds of millions of galaxies and looking for the statistical correlations that reveal dark energy's influence on the distribution of matter, Roman will probe dark energy's behavior with a precision that no previous instrument has approached. The second is baryon acoustic oscillations, the same cosmic ruler that DESI has been measuring from the ground, but now measured from space with infrared sensitivity that allows Roman to observe galaxies at higher redshifts than ground-based surveys can easily reach. Higher redshifts mean looking further back in time. Further back means more leverage on how dark energy was behaving in the early universe, which is exactly where the DESI hints suggest the most interesting physics is happening. The third is Type 1a supernovae. Roman will discover and characterize supernovae at distances and redshifts that no previous survey has been able to reach systematically. Remember that the original 1998 discovery came from measuring dozens of supernovae. DESI's combined analysis used datasets of hundreds to a few thousand. Roman is expected to discover and characterize potentially hundreds of thousands of Type 1a supernovae over its 5-year primary mission. The statistical power of that sample, applied to the same cosmological distance measurements that revealed the accelerating expansion in 1998, will either confirm the DESI hints of evolving dark energy or constrain them to near non-existence. 3 independent techniques, hundreds of millions of galaxies, space-based precision unaffected by Earth's atmosphere, 5 years of operations. "Within our lifetimes," said Nikki Fox, NASA's Associate Administrator for Science, "a great mystery has arisen about the cosmos. Why the expansion of the universe seems to be accelerating. There is something fundamental about space and time we don't yet understand, and Roman was built to discover what it is." Roman's construction was completed on November 25, 2025. After completion, the telescope moved into final testing. On April 21, 2026, NASA Administrator Jared Isaacman announced at a news conference at Goddard that the mission is now targeting a launch as early as September 2026, 8 months ahead of the committed deadline of May 2027. The testing has gone well. The hardware is performing. The launch preparations are on track. A SpaceX Falcon Heavy rocket will carry Roman to its destination, the Sun-Earth second Lagrange point, 1 million miles from Earth, where it will join Euclid in that gravitationally stable vantage point. Once there, it will begin commissioning, testing and calibrating its instruments before beginning science operations. Within a year of launch, possibly by late 2027 or 2028, Roman's first dark energy measurements will start to arrive. And given the instrument's power and the 3-technique approach, those measurements will carry real weight in settling the question of whether dark energy is evolving. Julie McEnery, Roman's senior project scientist at NASA Goddard, put it this way: "In the mission's first 5 years, it's expected to unveil more than 100,000 distant worlds, hundreds of millions of stars, and billions of galaxies. We stand to learn a tremendous amount of new information about the universe very rapidly after Roman launches." Billions of galaxies. That's not a rounding error.
That's the scale of what's coming. The Vera C. Rubin Observatory, the Southern Skies contribution. We encountered the Vera C. Rubin Observatory in the Dark Matter video, the ground-based survey telescope in the Andes Mountains of Chile, named for the astronomer who proved dark matter was real, built around the largest digital camera ever constructed at 3,200 megapixels. It released its first images on June 23, 2025, and began its legacy survey of space and time, the LSST, shortly after. For dark energy, Rubin contributes primarily through two channels. The first is weak gravitational lensing, applied to the billions of galaxy images it will collect over its 10-year survey. The sheer scale of the Rubin dataset, billions of galaxies, each measured multiple times over a decade, gives it extraordinary statistical power for measuring the subtle correlations in galaxy shapes that reveal dark energy's influence on large-scale structure. The second is supernovae. Rubin scans the southern sky repeatedly, every few nights, and in doing so, it catches supernovae at various stages of their brightening and fading. Over 10 years, Rubin is expected to discover and monitor hundreds of thousands of Type 1a supernovae, comparable to Raman's yield, but from the ground in the optical wavelengths, covering different areas of sky and different systematic effects. The combination of Rubin's supernova sample with Raman's infrared supernova sample will produce a dataset of unprecedented power for constraining dark energy's equation of state. Rubin's contributions to dark energy science will grow progressively over the decade-long survey. The first major data releases are expected within a year or two of the survey start. The full statistical power of the dataset, the combination that will really nail down dark energy's behavior, will emerge as the years accumulate. The Atacama Cosmology Telescope and CMB experiments. From high in the Atacama Desert of Chile, one of the driest places on Earth, where the atmosphere is thin enough and dry enough to allow precise measurements of microwave radiation, the Atacama Cosmology Telescope has been measuring the cosmic microwave background with extraordinary precision. ACT's measurements of the CMB have already contributed to the dark energy tension story. Combined with DESI data and Planck results, the ACT data was part of the combination that produced the most significant hints of evolving dark energy in the March 2026 analysis papers. Future CMB experiments, the Simons Observatory, currently being built at the same Atacama site, and the proposed CMBS-4 experiment, a massive collaboration of ground-based CMB telescopes, will improve on ACT's measurements substantially. More precise CMB data means better calibration of the early universe baseline against which dark energy measurements are compared. It means tighter constraints on the Hubble tension. It means more leverage on the question of whether there was early dark energy, late dark energy evolution, or something else entirely driving the discrepancies in the standard model.
What we're actually waiting for. Let's be concrete about the timeline of what's coming, because the abstract promise of more data is less useful than a specific picture of what measurements arrive when. In 2026, Roman launches begins commissioning. DESI continues extended observations. Rubin's survey deepens. Several DESI analysis papers on structure and evolution expected. Euclid continues survey, deeper datasets accumulating. In 2027, DESI releases first dark energy results from complete 5-year survey. This is the single most anticipated result in cosmology. Roman begins science operations, first early results possible by late 2027. Euclid's cosmological constraints begin to sharpen. In 2028, Roman's first dark energy measurements arrive with meaningful statistical power. DESI extended survey continues. The combination of DESI 5-year results, early Roman data, and Euclid's deepening survey begins to paint a coherent picture. In 2029 and beyond, Roman's full statistical power comes online. Rubin's accumulated dataset grows substantially. The combination of all these instruments, independent techniques, independent systematics, complementary wavelength coverage, and sky coverage, produces the most precise picture of dark energy ever assembled. By the early 2030s, if the DESI hint of evolving dark energy is real and survives the scrutiny of all these instruments, it will not merely have crossed the 5 sigma threshold. It will have been confirmed by multiple independent techniques to a degree of certainty that leaves no serious room for doubt. The cosmological constant will have been replaced as the complete picture. Dark energy's evolution will be established. The TIE model, or something like it, will be on solid observational footing. And the expiration date of the universe will no longer be a compelling prediction. It will be a scientific conclusion. If the hint doesn't survive, if Roman and Euclid and the full DESI dataset all point back toward a constant dark energy, then the cosmological constant is confirmed with the same unprecedented precision. Forever expansion. No crunch. The receipt was wrong. Either way, we get an answer. A real answer. Not a hint, not a tension, not a 3.9 sigma deviation that might or might not be real. An answer. Within the next decade, humanity will know, with the same level of certainty that we know the age of the universe, the speed of light, the mass of the electron, whether dark energy is constant or evolving, whether the universe is eternal or mortal. We are, right now, in the last years of not knowing. There's something worth sitting with in that. For most of human history, the question, how does the universe end, was metaphysical, the province of religion and philosophy. Cosmology, for most of the discipline's existence, dealt in scenarios and possibilities rather than specific predictions. The universe might expand forever, or it might collapse. Depending on how much matter there was, on whether dark energy was constant or evolving, on parameters that were simply unmeasurable with the instruments available. That era is ending. Not because we've found the answer yet, we haven't, but because we're about to have the tools to find it. The instruments that will measure dark energy's behavior with sufficient precision to settle the question are either built, in orbit, or being loaded onto a Falcon Heavy rocket. We are the first generation of humans who will live to see this question answered. Not our grandchildren, not some distant future civilization. Us, the people watching this video right now. The first dark energy results from DESI's complete 5-year survey will be released in 2027. If you're watching this in 2026, that's next year. If Roman launches on schedule in September 2026, which the latest NASA statements suggest is achievable, its first science measurements will begin flowing within months of launch. Euclid is already in orbit, already observing, already accumulating data that will contribute to the answer. The wait is almost over. And when the answer comes, whatever it is, it will be one of the most significant moments in the history of human knowledge. Not just cosmological knowledge, all knowledge. Because the question being answered is not merely what is dark energy, it's is the universe eternal or does it end? It's is there a final moment, a last second, a closing of the brackets that began with the Big Bang? It's
How does the story end? Science has been building toward this question for a century. Einstein's cosmological constant in 1917. Hubble's expanding universe in 1929. The accidental discovery of acceleration in 1998. The Planck satellite's cosmic recipe in 2013. DESI's 5 years of galaxy mapping concluded on April 14, 2026. Each step was necessary. Each step built on the ones before. And now, at the end of this chain of discovery, we're close enough to the answer that you can almost feel it.
The receipt is in our hands. We're reading it carefully. And in the next few years, we're going to find out whether the expiration date is real. Which brings us, finally, to the question that has been waiting patiently at the back of everything we've discussed. Not what dark energy is, not when the universe ends, but what it means. What does it mean to be the species that found the receipt? What does it mean to live in a universe that might be mortal? What does it do to a mind, to a civilization, to know that the stage on which everything plays out is not eternal, that the story has a final chapter, that the backdrop of all of human experience is itself temporary? That's where we're going, and it's the most important part of the story. Stop for a moment. Not to summarize, not to recap what we've covered, just to stop and be here, in the actual present moment of the universe's life. 13.8 billion years in, roughly 40% through, if the receipt is right. Sitting on a pale blue dot, orbiting an unremarkable star in the outer arm of a spiral galaxy, surrounded by a vast, invisible halo of something we can't identify. Inside a universe that is expanding and accelerating and might be heading toward a collapse that will erase every trace that any of this ever existed. Just sit with that for a second. There's a version of this ending that reaches for comfort, that points to the 19.5 billion years remaining and says, plenty of time, don't worry, nothing to see here. There's another version that reaches for drama, end-of-the-world language, existential crisis, the universe as a ticking bomb. I don't want either of those, because both of them are ways of not actually feeling what this means, ways of moving past the strangeness instead of staying inside it long enough for it to change something. So let's stay inside it. The universe has a lifespan. Maybe. We don't know yet with certainty. The 2027 DESI results, the Roman measurements, the Euclid data, will tell us more. But the possibility is now a serious scientific proposition, grounded in real data, published in peer-reviewed journals, built by physicists who spent their careers thinking carefully about the structure of reality. The possibility that everything, all of it without exception, ends in approximately 33.3 billion years is no longer a philosophical speculation. It's a hypothesis, a testable, falsifiable, data-driven hypothesis. And living with that hypothesis, even provisionally, changes something. Let's start with what it means for our place in time. For almost all of human history, people imagined the universe as eternal. Not just very old, eternal, without beginning or end. The stars were fixed. The cosmos was permanent. Change happened at the human scale. Civilizations rose and fell, seasons turned, generations passed. But the backdrop against which all of this played out was forever. That changed in stages. The first stage was Hubble's discovery in 1929 that the universe is expanding. If it's expanding now, it was smaller in the past. Run the expansion backward in time and you arrive at a beginning, a moment of creation, the Big Bang. The eternal universe was replaced by a universe with a beginning. That was philosophically enormous. Every religion, every mythology, every cosmology had grappled with the question of origins. Suddenly, science had an answer. 13.8 billion years ago, it started. The second stage was the 1998 discovery of dark energy, the accelerating expansion. This gave us not just a beginning, but a trajectory. The universe isn't just expanding, it's speeding up. The long-term destiny in the cosmological constant model was an ever-expanding, ever-cooling, ever-emptying void. The heat death, the long freeze, a universe spread so thin over such vast distances that nothing interesting could ever happen again. Eternal expansion into eternal darkness. Not a dramatic end, just a slow, cold disappearance of everything meaningful. The third stage, the one we might be living through right now as the DESI results come in and the TIE model sits on the table, is the possibility that the universe has not just a beginning, but an end. A real end. A finite lifespan. A closing bracket. Beginning, middle, end. That's the structure of a story. And humanity has spent its entire existence telling stories, finding meaning in narrative arcs, in the shape of things, in the movement from start to finish. We are, perhaps more than anything else, a storytelling species. We understand the world through narrative. And the universe, it turns out, might have one. We are 40% through the middle. Think about what it means to be at the 40% mark of a story. In any narrative, a novel, a film, a life, the 40% point is where things are still rich with possibility, but the shape of what's coming is beginning to be visible. The beginning is clearly behind you. The end is not yet close, but it exists. You're in the part of the story where complexity is at its peak, where all the threads that were introduced at the start are still active, where the consequences of early choices are playing out, where things are most densely alive with meaning. The universe at 13.8 billion years is exactly that. 2 trillion galaxies, billions of stars still being born, planetary systems forming. Whatever life exists, wherever it exists, in the middle of whatever it's doing. The universe at the 40% mark is not declining. It's not on its way out yet. It's at peak complexity, peak density of possible experience. And we're here for it.
Not by choice, obviously. We didn't select our position on the cosmic timeline any more than we selected our position in the Milky Way or on the surface of the Earth. But we happen to be here, now, at this specific moment in the universe's story. And the question of what it means to be conscious, observing creatures at this particular point in cosmic time is one that I don't think we've fully absorbed yet. Here's one way to think about it that I find genuinely strange and genuinely beautiful. The universe is losing information. Not in the trivial sense of entropy increasing, though that's also true. I mean something more specific. Dark energy, even in the cosmological constant model,
where it's constant and the universe expands forever, is actively making the universe less knowable. Every year, galaxies at the edge of our observable universe are receding faster. Their light, which was already stretched into radio waves by the expansion, is being stretched further. Their recession speed is increasing. Eventually, in the standard forever expansion model, galaxies will be receding faster than light. Their light will never reach us again. They will cross our cosmic horizon and vanish. Not destroyed, not gone from the universe, just permanently unreachable, causally disconnected from us, existing beyond a boundary that no signal, no information, no observation can ever cross in either direction. This is already happening. It has been happening for billions of years. Galaxies are disappearing from our observable universe right now. Not in the dramatic way, not winking out, but slowly, their light redshifting toward longer and longer wavelengths, their signals weakening and fading over millions of years before finally becoming undetectable. The night sky of the very far future, in the heat-death model, trillions of years from now, will be nearly empty. Every galaxy outside our local group will have disappeared beyond the horizon. The Milky Way-Andromeda merger, Milkomeda, will be an island in an essentially empty universe. No other galaxies visible. No evidence of the cosmic web of filaments and voids that we can map today. No way for any civilization that might exist then to know that there were once 2 trillion galaxies in the observable sky. No way to detect the cosmic microwave background, which will have been redshifted into wavelengths so long they're unmeasurable. No way to reconstruct the Big Bang. No way to know that the universe had a beginning, because all the evidence for that beginning will have been stretched beyond detection by the expansion. The universe is erasing its own history. Slowly, persistently, one galaxy at a time. And here, now, at the 40% mark, we can still see almost all of it. We can map the cosmic web. We can detect the CMB. We can observe galaxies at the edge of the observable universe whose light left before the Earth formed. We can read the universe's autobiography. We are living at the most information-rich moment the universe will ever offer any observer. The evidence is all still here. The story is still legible. That's not a coincidence in any mystical sense. Conscious observers capable of doing cosmology require billions of years of stellar evolution to produce the heavy elements, carbon, oxygen, nitrogen, that biology requires. They require stable planetary environments maintained for hundreds of millions of years. They require the kind of cosmic conditions that only exist in the middle phase of the universe's life. You couldn't have cosmology-capable life in the first billion years. The universe was too hot, too metal-poor, too young. You probably couldn't have it in the last billion years of the universe's life, if the crunch is coming, because conditions would be deteriorating. The window for observers is the middle. We're in the middle. We're in the window. Now let's talk about something that doesn't get said enough in science communication about topics like this. Uncertainty is not failure. We don't know what dark energy is. We don't know if the universe is finite or infinite in duration. We don't know whether the DESI hints are real or statistical noise. We don't know whether the big crunch is coming or whether the universe expands forever. We have competing models, unresolved tensions, a 10 to the power of 120 gap between theory and observation that has resisted every attempt at resolution for decades. That's not physics failing, that's physics working. Science at the frontier is always uncertain. The certainties, the things we know well enough to build technology on, to stake lives on, to write into textbooks without hedging, are the old discoveries. The things that have been tested 1,000 times, confirmed by independent methods, survived every attempt at falsification. The uncertainty is where the action is. The uncertainty is the frontier. Dark energy is the frontier. The biggest, most consequential, most stubbornly mysterious frontier in all of science. And we're not lost there. We have specific instruments, specific measurements, specific predictions, specific timelines for when the uncertainty will resolve. We know what data we need. We've built the machines to collect it. We know when the results will come. That's not uncertainty in the sense of being adrift. That's uncertainty in the sense of standing at the edge of what's known, looking at what's next, with the tools in hand to take the next step. There's a quote from Michael Turner, the man who named dark energy, that captures this. He said, "Dark energy is the most profound mystery in all of science." And then he said something else that's less often quoted. Until we understand it, we can't sensibly speculate about the destiny of the universe. He said that over 20 years ago. We're closer now. Not close enough to have the answer, but closer. The destiny of the universe is no longer something we can't speculate about sensibly. We're speculating, carefully, quantitatively, with specific models and specific predictions. And we're about to find out which speculation was right. That's progress. Genuine, hard-won, extraordinary progress. Let me ask you something that I've been sitting with throughout this entire video. Does it change anything to know that the universe might end? Not for you personally, not today, not in any practical sense. The Big Crunch is 19.5 billion years away, if it's coming at all. The sun will burn out long before then. The Earth will be gone. Whatever humanity becomes, or whatever comes after humanity, will face these questions in conditions we can't imagine from here. Nothing about your life, your choices, your relationships, your work changes because of a 33.3 billion year expiration date. But does knowing change something deeper? Something about how you relate to the cosmos? I think it might. Here's why. The idea of an eternal universe is, in a strange way, distancing. If the universe is forever, then the present moment is cosmically negligible, a speck in an infinite ocean of time. Nothing that happens now or ever carries any particular weight against the backdrop of eternity. The infinite absorbs everything, makes everything equally small. A finite universe is different. If the universe has a lifespan, 33.3 billion years or some other specific number, then every moment in that lifespan has a relative position, a meaning in the structure of the whole. The first 13.8 billion years happened. The middle is now. The remaining 19.5 billion years are ahead. These aren't arbitrary divisions. They're chapters in a story that has a shape. And we're in the chapter that has consciousness in it.
The chapter where matter organized itself into structures complex enough to look back at the whole and ask what it is. The chapter where physics got done by beings made of physics. Where the universe, through the improbable mechanism of biological evolution on at least one small planet, developed the capacity to study itself. That might not be philosophically special in any cosmic sense. The universe doesn't know we're here. It doesn't care about the DESI results. It doesn't have a stake in whether we figure out dark energy. The physics plays out the same whether or not anyone is watching. But it feels different from the inside. There's a detail about the DESI survey completion that I keep coming back to. On the night of April 14, 2026, the 5,000 fibre optic eyes of DESI locked onto a patch of sky near the Little Dipper. Every 20 minutes, they gathered photons that had been travelling toward Earth for billions of years. Light that left its source before our planet existed, before our sun existed, before the Milky Way had its current shape. Ancient light, carrying information about how fast the universe was expanding at the moment it was emitted, arriving after a journey so long that the source galaxy has long since aged beyond recognition. And on the other end of that light, on a mountain in Arizona, at the end of a fibre optic cable thinner than a human hair, in a spectrograph that spread the light into its component wavelengths and recorded what it found, there was a machine built by humans, pointed by human hands, operated by scientists who drove to work that morning, drank coffee, answered emails, and then spent the night collecting the oldest available evidence about the nature of the force that might end the universe. That contrast between the cosmic scale of what was being measured and the human scale of who was measuring it is, I think, the most important thing about dark energy science. Not the 10 to the 120 problem, as staggering as it is. Not the Big Crunch prediction, as dramatic as it is. Not the 6 sigma Hubble tension, or the 3.9 sigma DESI deviation, or the 47 million galaxies on the map. The most important thing is that we're doing this at all. That a species that didn't exist 300,000 years ago, that was drawing on cave walls 40,000 years ago, farming 10,000 years ago, writing 5,000 years ago, has built machines sensitive enough to measure the energy density of empty space across 11 billion years of cosmic history, has developed mathematical frameworks precise enough to predict that the universe ends in 33.3 billion years, based on percent-level variations in the BAO scale measured in galaxy spectra, has put a satellite 1 million miles from Earth specifically to observe 1 billion galaxies and characterize the nature of the dominant ingredient in reality. That's what consciousness does, given enough time and enough curiosity. It figures things out. It asks the hardest questions and builds the tools to answer them. It looks at a universe that has no obligation to be comprehensible and discovers over and over again that it is. Not completely, not yet, maybe not ever fully, but more so every decade than it was the decade before. That's not nothing. That's extraordinary. Let me tell you what we don't know, because ending on false certainty would be the wrong note. We don't know what dark energy is. After 26 years and billions of dollars of instruments and the careers of thousands of scientists, the fundamental nature of the force that dominates the universe is unknown. We have models, we have mathematical descriptions, we have the cosmological constant as a label,
We don't have a physical explanation that connects dark energy to the rest of physics, that tells you what produces it, what it's made of, why it has the value it has, and not a value 10 to the power of 120 times larger. We don't know if the universe ends. The DESI hints are real and significant. They might strengthen into a discovery. They might not. The 2027 results from the full DESI 5-year survey, the Roman measurements, the Euclid data, all of these will tell us more. They will not necessarily tell us everything. We don't know if the TIE model is right, even if dark energy evolves. Evolving dark energy is necessary for the big crunch in this framework, but it's not sufficient. The specific form of evolution, a negative underlying cosmological constant masked by a decaying scalar field, is one possibility among several. The data will constrain the options, but may not uniquely identify the mechanism for some time. We don't know what happens at the singularity. If the big crunch occurs, the equations of general relativity break down at the final moment. What quantum gravity does there, whether the crunch is truly an end or a transition to something else, a bounce into a new universe, a cycle that has already happened infinitely many times, is beyond the reach of current physics. And we don't know whether there's life elsewhere in the universe that is doing what we're doing right now. Looking up, asking the same questions, building their own DESI, their own Euclid, their own Roman telescope, sitting with the same uncertainty, wondering the same things, reading the same receipt and trying to figure out if it's real. We don't know any of that. But here's what we do know. The universe is 13.8 billion years old. It is made of 4.9% things we understand, 26.8% things we're searching for, and 68.3% something we cannot identify that is pushing everything apart at an accelerating rate, and that may, if the latest data is right, be weakening, losing its grip on the cosmos, in a way that will eventually let gravity back into the contest and bring everything crashing back down. We know that 2 teams of astronomers found this out by accident in 1998, while looking for something completely different, using dead stars as measuring sticks across billions of light-years of space. We know that Einstein accidentally discovered the mathematical description of this force in 1917, called it his biggest mistake, threw it away, and died not knowing he was right. We know that the leading theoretical explanation for dark energy is off by 10 to the power of 120, the worst prediction in the history of physics, and that nobody has solved this problem in the decades since it was clearly articulated. We know that a physicist at Cornell ran the latest data in 2025 and got a number: 33.3 billion years. We know that the universe is 13.8 billion years into that span. We know that means we're at roughly the 40% mark. We know that 19.5 billion years of possible future stretches ahead, full of possibilities we cannot imagine, developments we cannot foresee, complexity that will dwarf everything that has happened so far. We know that right now, today, the largest map of the universe ever made has just been completed by a machine on a mountain in Arizona. That a satellite in orbit 1 million miles from Earth is mapping 1 billion galaxies. That a telescope completed in November 2025 is being prepared for a launch in September 2026 that will, within a few years, either confirm the expiration date or show
that it was a misreading of the data. We know that we're alive at the specific moment in cosmic history when the question, "Does the universe end?" transitions from philosophy to science, when the answer moves from unknowable to measurable, when the receipt goes from illegible to readable. We are 40% through a story whose ending we are just now beginning to be able to read. And we are, somehow, improbably, against all the odds of cosmic scale and biological contingency, the part of the universe that is doing the reading. The universe doesn't know it has an expiration date. We do, or we're about to. And that specific fact, that a collection of atoms organized by evolution into conscious beings on a small planet has looked up at the cosmos and started to understand the shape of the whole thing, including the ending, is either the most remarkable coincidence in 13.8 billion years of cosmic history, or it's what it looks like when the universe, after enough time, develops the capacity to know itself. Either way, it's something. 33.3 billion years. We're 40% through. Make of that what you will.